is at safety, the derail operated with the signal is closed and the line is continuous. This combination of signals and derail coacting serves efficiently to prevent collisions at crossings, although trains may be occasionally derailed in accomplishing that end. The preceding explanations of the use of signals and derail apply to a train that may approach the crossing in either direction on either track, as is obvious from an inspection of the diagram itself. 283. Signaling at a double-track crossing. In the case of a double-track crossing, the arrangement of signals and derails is precisely the same as for a single-track crossing, each set of signals shown in Figure 15 covering one track. In other words, the line of single track is to take the place of each rail with its set of signals in that figure. There will be but 4 derails, one for each track only on the approach to the crossing. The working of the signals with the derails is precisely the same as has already been explained for the single-track crossing. Figure 15. Figure 16. 284. Signaling for double-track junction and crossover. Figure 16 represents a skeleton diagram of signals required for a junction of 2 double-track roads and a crossover. This arrangement covers the use of switches. The location of signals and signal cabin as shown is self-explanatory, after what has already been stated in connection with single and double-track crossings. It will be observed that the home signals for both the westbound main and branch tracks are identical in location, and are shown by the solid double flag, the distance signal being shown by its notched end at a considerable distance back of the double home signal. It will, furthermore, be observed that at each home signal there is a derailing switch interlocked, in the lock-and-block system presently to be explained, with the home signals operated simultaneously with them. If, therefore, an engineman attempts to run his train past a home signal set at danger, the result will be the derailment of his train, thus brought to rest before it can make any collision with another. It is obvious in this case that if the switches from the main to the branch tracks or at the extremities of the crossover are worked independently, they must be operated directly in connection with the signals. For complete protection, they should be interlocked with the signals so that it would be impossible to clear any signal without simultaneously setting the switches consistently with those signals. The diagram exhibits clearly the indications which must be made in order to effect any desired train movement at such a junction of tracks. 285. General observations. Similar arrangements of signals, derails, or switches must be made wherever switches, crossovers, and junctions are found, the detailed variations of those signals and switches being made to meet the individual requirements of each local case. The combinations of switches and switch signals frequently become very complicated in yards where the tracks are numerous and the combinations exceedingly varied, in order to meet the conditions created by the movement of trains into and out of the yard. The preceding explanations are intended only to give a clear idea of the main features of signaling, in order to secure the highest degree of safety and facility in the movement of trains over a modern railroad. While they exhibit the external or apparent combinations of signals for that purpose, they do not touch in detail and scarcely in general upon the mechanical appliances found in the signal cabin and along the tracks required to accomplish the necessary signal movements. The considerations in detail of those appliances would cover extended examinations of purely mechanical, electrical, pneumatic, and electropneumatic combinations too involved to be set forth in any but the most extended and careful study. They have at the present time been brought to a wonderful degree of mechanical perfection and afford a field of most interesting and profitable study, into which, however, it is not possible in these general statements of the subject to enter. Figure 17. 286. Interlocking machines. The earliest machine perfected for use in this department of railroad signaling was the Saxby and Farmer interlocking machine, first brought out in England and subsequently introduced in this country between 1874 and 1876. This machine has been much improved since and has been widely used. Other interlocking machines have also been devised and used in this country in connection with the most improved systems of signaling, until at the present time a high degree of mechanical excellence has been reached. The interlocking machine in what is called the lock-and-block system of signaling is designed to operate signals, or signals in connection with switches, derailing points, or other dangerous track features, so as to make it impossible for a signalman to make a wrong combination, that is, a combination in which the signals will induce the engineman to run his train into danger. The signals and switches or other track details are so connected and interlocked with each other as to form certain desired combinations by the movement of designated levers in the signal cabin or tower. These combinations are predetermined in the design and connections of the appliances used, and they cannot be changed when once made except by design or by breakage of the parts. They cannot be deranged by any action of the signalman. He may delay trains by awkward or even wrong movement of levers, but he cannot actually clear his signals for the movement of a train without simultaneously giving that train a clear and safe track. As has been stated, he cannot organize an accident. Figures 17 and 18 show banks or series of levers belonging to interlocking machines. As is evident from these figures, the levers are numerous if the machine operates the switches and signals of a large yard, for the simple reason that a great many combinations must be made in order to meet the requirements of train movements in such a yard. The signalman, however, makes himself acquainted with the various combinations requisite for outgoing and incoming trains and the possible movements required for the shifting or hauling out of empty trains. He has before him diagrams showing in full the lever movements which must be made for the accomplishment of any or of all these movements, and he simply follows the directions of the diagrams and his instructions in the performance of his duty. He cannot derange the combinations, although he may be slow in reaching them. The locking frame which compels him to make a clear track whenever his signals give a clear indication to the engine man lies below the lower end of the levers seen in the figures. The short arms of the levers carry tappets with notches in their edges into which fit pointed pieces of metal or dogs. The arrangement of these notches and dogs is such as to make the desired combinations and no others. It will be observed that a spring latch handle projects from a point near the upper end of each lever where the latter is grasped in operating the machine. This spring latch handle must be pressed close to the lever before the latter can be moved. The pressing of the spring latch handle against the lever effects a suitable train of unlocking before which the lever cannot be moved and after which it is thrown over to the full limit and locked there. The desired combination for the movement of the train through any number of switches may require a similar movement of a number of levers, but the entire movement of that set, as required, must be completely effected before the signals are cleared, and when they are so cleared the right combination forming a clear track for the train, and that one only, is secured. These meager and superficial statements indicate in a general way, however imperfectly, the ends attained in a modern interlocking machine. They secure for railroad traffic as nearly as possible an absolutely safe track. They eliminate, as far as it is possible to do so, the inefficiency of human nature, the erratic, indifferent, or willfully negligent features of human agency, and substitute therefore the certainty of efficient mechanical appliances. In some and perhaps many states grade crossings are required by statute to adopt measures that are equivalent to the most advanced lock-and-block system of signaling. So vast has become railroad traffic upon the great trunk lines of the country that it would be impossible to operate them at all without the perfected modern systems of railroad signaling. They constitute the means by which all train movements are controlled, and without such systems great modern railroads could not be operated. Figure 18. The swiftly moving limited express passenger trains, equipped with practically every luxury of modern life, speed their way so swiftly and smoothly over many hundreds of miles without the incident of an interruption, and in such a regular and matter-of-fact way, that the suggestion of an intricate system of signaling governing its movements is never thought of. Yet such a train moves not a yard over its track without the saving authority of its block signals. If the engine man were to neglect even for a mile the indication of the semaphore, he would place in fatal peril the safety of his train and of every life in it. 287. Methods of applying power in systems of signaling. The mechanical appliances used in accomplishing these ends are among the most efficient in character and delicate yet certain in motive power which engineering science has yet produced. The electric circuit formed by the rails of the track plays a most important part, particularly in securing the safety of the rear of the train and making it absolutely certain whether even rear cars that may have broken away have either passed out of the block or are still in it. The electric circuit in one application or another was among the earliest means used in railroad signaling. Electric power is also used in connection with compressed air for the working of signals. Among the latest and perhaps the most advanced types of lock-and-block signaling is that which is actuated by low-pressure compressed air, the maximum pressure being 15 pounds only per square inch. The compressed air is supplied by a simple compressor, and it is communicated from the signal cabin to the most remote signal or switch by pipes and suitable cylinders fitted with pistons controlled by valves, thus affecting the final signal or switch movements. It has been successfully applied at the yard of the Grand Central Station in New York City and at many other similar points. In this connection, it is interesting to observe that while the original Saxby and Farmer interlocking machine was installed from England in this country, as has already been observed, about 1875, American engineers have within a year reciprocated the favor by furnishing and putting in place most successfully in one of the great railroad yards of London the first low-pressure pneumatic lock-and-block system, 8, found in Great Britain. 288, train staff signaling. The lock-and-block system gives the highest degree of security attainable at the present time for double-track railroad traffic, but the simpler character of the single-track railroad business can be advantageously controlled by a somewhat simpler and less expensive system, which is a modification of the old train staff method. It is one of the machine methods of signaling. The type which has been used widely in England, Australia, and India, and to some extent in this country is called the Webb and Thompson train staff machine, shown in Figure 19. It will be observed that the machine contains 10 staffs, 18 to 20 inches long and 1 to 1¼ inches in diameter, but as many as 15 are sometimes used. These staffs can be removed from the machine at one end of a section of the road at which a train is to enter, only by permission from the operator at the farther end of the section. If the station at the entrance to that section is called A, and the station at the farther end X, the following description of the operation of the instrument is given by Mr. Charles Hansel in a very concise and excellent manner. Figure 19. Webb and Thompson train staff machine. When a train is ready to move from A to X, the operator at A presses down the lever which is seen at the bottom of the right-hand dial, sounding one bell at X, which is for the purpose of calling the attention of the operator at X to the fact that it desires to send a train forward. The operator at X acknowledges the call by pressing the lever on his instrument, sounding a bell in the tower at A. The operator at A then asks permission from X to withdraw staff by pressing down the lever before mentioned 3 times, giving 3 rings on the bell at X, and immediately turns his right-hand pointer to the left, leaving it in the horizontal position pointing to the words for staff, indicating that he desires operator at X to release his instrument so that he can take a staff or train order from it. If there is no train or any portion of a train between A and X, the holding down of the lever at X closes the circuit in the lock magnets at A, which enables the operator at A to withdraw a staff. As soon as this staff is removed from A turns the left-hand pointer to the word staff out, and in removing this staff from the instrument a galvanometer needle which is seen in the center of the instrument between the 2 dials vibrates, indicating to the operator at X that A has withdrawn his staff. X then releases the lever which he has held down in order that A might withdraw a staff and turns his left-hand indicator to staff out, and with this position of the instrument a staff cannot be withdrawn from either one. The first method of delivering this staff to the engineer as a train order was to place it in a staff crane, which crane was located on the platform outside of the block station. With the staff in this position, it has been found in actual practice that the engine man can pick it up while his train is running at a speed of 30 miles per hour. A second staff cannot be removed from A nor a staff removed from X until this staff which was taken by the engine man in going from A to X is placed in the staff instrument at X. Consequently, the delivering of a staff from A to the engine man gives him absolute control of the section between A and X. This train order staff also controls all switches leading from the main line between A and X, for with the style of switch stand which we have designed for the purpose the trainman cannot open the switch until he has secured the staff from the engine man and inserted it in the switch stand, and as soon as he throws the switch lever and opens the switch he fastens the train staff in the switch stand, and it cannot be removed until the switchman has closed and locked the switch for the main line. When this is done he may remove the train staff and return it to the engine man. It will thus be seen that this train order, in the shape of a staff, gives the engine man absolute control over the section, and also ensures that all switches from the main line are set properly before he can deliver the train staff to the instrument at X in order that the operator at X may be assured that the entire train has passed his station. We may divide the staff in 2 and deliver one half to the engine man and the other half to the trainman on the caboose or rear end of the train, and It will be necessary for the operator at X to have the two halves so that he may complete the staff in order to insert it into the staff instrument at X. As it is impossible to insert a portion of the staff, it must be entirely complete before it can be returned to the staff instrument. Instead of using the entire staff as a whole or in two parts, Mr. Hansel suggests that one or more rings on the body of the staff be removed from the latter and given to the engineman or other trainman to be placed upon a corresponding staff at the extreme end of the section. This would answer the purpose, for no staff can be inserted in a machine unless all the rings are in their proper positions. These rings can be taken up by a train moving at any speed from a suitable crane at any point alongside the track. For a rapid movement of trains on a single-track railroad under this staff system, an engineman must know before he approaches the end of the section whether the staff is ready for delivery to him. In order to accomplish that purpose, the usual distant and home signals may readily be employed. The distant signal would show him what to expect, so that he would approach the entrance to the section either at full speed or with his train under control according to the indication. Similarly, electric circuits may be employed in connection with the staff or rings and the control of signals which it may be desired to employ. The electric train staff may also be used in a permissive block system, the section of the track between stations A and X constituting the block. In Figure 19, showing the machine, a horizontal arm is seen to extend across its face and to the right. This is the permissive attachment which must be operated by the special staff shown on the left half of the machine about midway of its height. If it is desired to run 2 or 3 trains or 2 or 3 sections of the same train from A before admitting a train at X in the opposite direction, the operator at A so advises the operator at X. The latter then permits A to remove the special staff with which the extreme right-hand end of the permissive attachment is unlocked and a tablet taken out. This tablet is equivalent to a train order and is given to the train immediately starting from A. A second tablet is given in a similar manner to the second section or train, and a third to the third section. The last section of train or train itself starting from A takes all the remaining tablets and the special staff for insertion in the machine at X. In this manner, head-to-head collisions are prevented when a number of trains are passing through the block in the same direction before the entrance of a train in the opposite direction. This system has been found to work satisfactorily where it has been used in this country, although its use has been quite limited. Evidently, in itself, it is not sufficient to prevent rear-end collisions in a block between trains moving in the same direction. In order to avoid such collisions where a train falls behind its scheduled time or for any reason is stopped in a block, prompt use must be made of rear flagmen or other means to stop or to control the movement of the first following train. Figure 20. The most improved form of high-speed train staff machine is shown in Figure 20, as made and installed by the Union Switch and Signal Company and used by a number of the largest railroad systems of the United States. In these machines the staffs are but a few ounces in weight. Chapter 23. 289, Evolution of the Locomotive. The evolution of the steam locomotive may be called the most spectacular portion of the development of railroad engineering. The enormous engines used at the present time for hauling both heavy freight and fast passenger trains possess little in common, in respect of their principal features, with the crude machines, awkward in appearance and of little hauling capacity, which were used in the early part of the 19th century in the beginning of railroad operation. The primitive and ill-proportioned machine, ungainly in the highest degree, designed and built by Trevithick as far back as 1803, was a true progenitor of the modern locomotive, although the family resemblance is not at first very evident. Several such locomotive machines were designed and operated between 1800 and 1829 when Stephenson's rocket was brought out. The water was carried in a boiler on a wagon immediately behind the engine, and the steam cylinder in those early machines was placed almost anywhere but where it now seems to belong. The rocket has some general features of resemblance to the machines built 70 years later, but when placed side by side it might easily be supposed that 700 years rather than 70 had elapsed between the two productions of the shop. After the famous locomotive trial in which Robert Stephenson distanced his competitors, the design of the locomotive advanced rapidly, and it was but a few years later when the modern locomotive began to be accurately foreshadowed in the machines then constructed. This was true both in England and the United States. The first steam locomotive in this country is believed to be the machine built by John Stevens at Hoboken, N.J., in 1825 and operated in 1825 to 27. This locomotive has practically the arrangement of boiler and cylinder which is found upon the modern contractors' engines used for pile driving, hoisting, and similar operations. It would certainly be difficult to imagine that it had any relation to the great express and freight locomotives of the present day. The rectilinear motions of the piston were transformed into the rotary motion of the wheels by means of gearing consisting of a simple arrangement of cogwheels. About the same time a model of an English locomotive called the Stockton and Darlington No. 1 was brought to the United States by Mr. William Strickland of Philadelphia. The next important step in American locomotive development was the construction of the locomotive John Bull for the Camden and Amboy Railroad Company in the English shops of Stephenson and Company in the years 1830 to 31. This machine has the general features, although not the large dimensions, of many modern locomotives. The cowcatcher is a little more elaborate in design and far-reaching in its proportions than the similar appendage of the present day, but the general arrangement of the firebox and boiler, the steam cylinders, the driving wheels, and smokestack is quite similar to a modern American locomotive. This machine, John Bull, and train made the trip from New York City to Chicago and return under its own steam in 1893. It was one of the prominent features of the World's Columbian Exposition. It rests in the National Museum at Washington, where it is one of the most interesting early remains of mechanical engineering in this country. One of the cars used in this train was the original used on the Camden and Amboy Road about 1836. Its body was used as a chicken coop at South Amboy, N.J., for many years, and was rescued from this condition of degradation for the purpose of the exposition trip in 1893. The original driving wheels had locust spokes and felloes, the hubs and tires being of iron. The locomotive George Washington was built, as a considerable number have been since, with one driving axle, and was designed to be used on heavy grades. This machine was built by William Norris and Sons of Philadelphia, who were the progenitors of the present great establishment of the Baldwin Locomotive Works. While the development of the locomotive was subjected to many vicissitudes in principles, general arrangement, and size in order to meet the varying requirements of different roads as well as the fancies or more rational ideas of the designers, its advance was rapid. As early as 1846 we find practically the modern consolidation type, followed in 1851 by the ordinary 8-wheel engine of which thousands have been constructed within the past 50 years. The first mogul built by the Baldwin Locomotive Works was almost if not quite as early in the field. Both these types of machines carry the principal portion of their weight upon the driving wheels and were calculated to yield a high tractive capacity, especially as the weights of the engines increased. The weight of the little John Bull was but 22,425 pounds, while that of the great modern machine may be as much as 267,800 pounds, with 53,500 pounds on a single driving axle. 290. Increase of locomotive weight and rate of combustion of fuel. The development of railroad business in the United States has been so rapid as to create rigorous exactions of every feature of a locomotive calculated to increase its tractive force. Any enhancement of train load without increasing the costs of the train force or other cost of movement will obviously lead to economy in transportation. In order that the locomotive may yield the correspondingly augmented tractive force, the weight resting upon the drivers must be increased, which means a greater machine and at the same time higher working pressures of steam. This demands greater boiler capacity and strength and a proportionately increased rate of combustion, so as to move the locomotive and train by the stored-up energy of the fuel transformed in the engine through steam pressure. The higher that pressure, the greater the amount of energy stored up in a unit of weight of the steam, and the greater will be the capacity of a given amount of water to perform the work of hauling a train. The greater the weight of train moved and the greater its speed, the more energy must be supplied by the steam, and, again, that can only be done with a correspondingly greater consumption of fuel. In the early days of the small and crude machines to which allusion has already been made, the simplest fuel was sufficiently effective. As the duties performed by the locomotive became more intense, a higher grade of fuel, i.e., one in which a greater amount of heat energy is stored per unit of weight, was required. Both anthracite and bituminous coal have admirably filled these requirements. The movement of a great modern locomotive and its train at an average rate of 30 to 60 miles per hour requires the combustion of fuel at a high rate and the rapid evaporation of steam at pressures of 180 to 225 or more pounds per square inch. The consumption of coal by such a locomotive may reach 100 pounds per minute, and 2 barrels of water may be evaporated in the same time. This latter rate would require over a gallon of water per second to be ejected through the stack as exhaust steam. Some of the most marked improvements in locomotive practice have been made practically within the past 6 or 7 years in order to meet these exacting requirements. While the operations of locomotives will obviously depend largely upon quality of fuel, speed, and other conditions, the investigations of Professor W. F. M. Goss and others appear to indicate that 12 to 14 pounds of water per hour may be evaporated by a good locomotive boiler per square foot of heating surface, and that 25 to 30 pounds of steam will be required per indicated horsepower per hour. 291. Principal parts of a modern locomotive. The principal features of a modern locomotive are the boiler with the smokestack placed on the front end and the firebox or furnace at the rear, the tubes, about 2 inches in diameter, through which the hot gases of combustion pass from the furnace to the smokestack, the steam cylinders with their fittings of valves and valve movements, and the driving wheels. These features must all be designed more or less in reference to each other, and whatever improvements have been made are indicated almost entirely by the relative or absolute dimensions of those main features. The boiler must be of sufficient size so that the water contained in it may afford a free steam production, requiring in turn a corresponding furnace capacity with the resulting heating surface. The latter is that aggregate surface of the interior chambers of the boiler through which the heat produced by combustion finds its way to the water evaporated in steam. It is composed almost entirely of the surfaces of the steel plates of the firebox and of the numerous tubes running through the boiler and parallel to its center, exposed to the hot gases of combustion and in contact with the water on the opposite sides of those plates. Evidently, an increase in size of the firebox with the correspondingly increased combustion will furnish a proportionally larger amount of steam at the desired high pressure, but an increase in the size of the firebox is limited both in length and in width. It is found that it is essentially impracticable for a fireman to serve a firebox more than about 10 feet in length. The maximum width of the locomotive limits the width of the firebox. Figure 21. 292. The wooden firebox and boiler. As the demand arose for an enlarged furnace, the width of the latter was restricted by the width between the driving wheel tires, less than 4 feet 6 inches. That difficulty was overcome by what is known as the Wooten firebox, which was brought out by Johnny Wooten of the Philadelphia and Reading Railroad about 1877, and has since been developed and greatly improved by others. The Wooten boiler with its sloping top and great width extending out over the rear driving wheels presented a rather curious appearance and was a distinct departure in locomotive boiler design. Figure 21 shows an elevation and 2 sections of the original Wooten type of boiler. It will be noticed that in front of the firebox there is a combustion chamber of considerable length, 2.5 to 3 feet long. This boiler was first designed to burn the poorer grades of fuel, such as coal slack, in which the combustion chamber to complete the combustion of the fuel was thought essential. By Wooten's device, i.e., extending the boiler out over the driving wheels, a much greater width of firebox was secured, but the height of the locomotive was considerably increased. It cannot be definitely stated just how high the center of the locomotive boiler may be placed above the track without prejudice to safety in running at high speeds, but it has not generally been thought best to lift that center more than about 9.5 feet above the tops of rails, and this matter has been held clearly in view in the development of the wide firebox type of locomotive boilers. Like every other new form of machine, the Wooten boiler developed some weak features, although there was no disappointment in its steaming capacity. It will be noticed in the figure that the plates forming that part of the boiler over the firebox show abrupt changes in curvature which induced ruptures of the stay bolts and resulted in other weaknesses. This boiler passed through various stages of development, till at the present time figures 22 and 23 show its most advanced form, which is satisfactory in almost or quite every detail. The sudden changes in direction of the plates in the first Wooten example have been displaced by more gradual and easy shapes. Indeed, there are few features other than those which characterize simple and easy boiler construction. The enormous grate area is evident from the horizontal dimensions of the firebox, which are about 120 inches in length by about 106 inches in breadth. The boiler has over 4,000 square feet of heating surface and carries about 200 pounds per square inch pressure of steam. The combustion chamber in front of the firebox has been reduced to a length of about 6 inches, just enough for the protection of the expanded ends of the tubes. The barrel of the boiler in front of the firebox has a diameter of 80 inches and a length of about 15 feet. The grate area is not far from 100 square feet. The improvements which have culminated in the production of this boiler are due largely to Mr. Samuel Higgins of the Lehigh Valley Road. Figure 22. Figure 23. 293, locomotives with wooden boilers. Figure 24 exhibits a consolidation freight locomotive of the Lehigh Valley Railroad, having the boiler shown in figures 22 and 23. This machine is one of the most efficient and powerful locomotives produced at the present time. The locomotive shown in figure 25 has a record. It is one used on the fast-reading express service between Philadelphia and Atlantic City during the season of the latter resort. It has run one of the fastest scheduled trains in the world and has attracted attention in this country and abroad. Its type is called the Atlantic and, as the view shows, it is fitted with the Wootton improved type of boiler. It will be noticed that the wide firebox does not reach out over the rear drivers, but over the small trailing wheels immediately behind them. This is a feature of wide locomotive firebox practice at the present time to which recourse is frequently had. There is no special significance attached to the presence of the small trailing wheels except as a support for the rear end of the boiler, their diameters being small enough to allow the extension of the firebox over them without unduly elevating the center of the boiler. Figure 24. The cylinders of these and many other locomotives are known as the Vauquelin compound. In other words, it is a compound locomotive, there being two cylinders, one immediately over the other, on each side. The diameter of the upper cylinder is much less than that of the lower. The steam is first admitted into the small upper cylinder and after doing its work there passes into the lower or larger cylinder, where it does its work a second time with greater expansion. By means of this compound or double-cylinder use of the steam a higher rate of expansion is secured and a more uniform pull is exerted upon the train, the first generally contributing to a more economical employment of the steam, which in turn means a less amount of fuel burned for a given amount of tractive work performed. Figure 25. In the early part of November, 1901, an engine of this type hauling a train composed of 5 cars and weighing 235 tons made a run of 55.5 miles between Philadelphia and Atlantic City at the rate of 71.6 miles per hour, the fastest single mile being made at a rate of a little less than 86 miles per hour. The power being developed by these engines runs as high as 1400 HP at high speeds and 2000 HP at the lower speeds of freight trains. The chief economic advantage of these wide firebox machines lies in the fact that varying different grades of fuel may be consumed. Indeed, there are cases where fuel so poor as to be unmarketable has been used most satisfactorily. With a narrow and small firebox, a desired high rate of combustion sometimes demands a draft strong enough to raise the fuel over the grate bars. This difficulty is avoided in the large firebox, where sufficient combustion for rapid steaming is produced with less intensity of blast. 294. Recent improvements in locomotive design. Concurrently with the development of the Wootton type of boiler, other wide firebox types have been brought to a high state of excellence. In reality, general locomotive progress within the past few years has been summed up by Mr. F. J. Cole as follows: A. The general introduction of the wide firebox for burning bituminous coal. B. The use of flues of largely increased length. C. The improvements in the design of piston valves and their introduction into general use. D. The recent progress made in the use of tandem compound cylinders. Figure 26. The piston valve, to which reference is made, is a valve in the shape of two pistons connected by an enlarged stem or pipe the entire length of the double piston, the arrangement depending upon the length of steam cylinder or stroke. It may be 31 or 32 inches. This piston valve is placed between the steam cylinder and the boiler, and is so moved by eccentrics attached to the driving wheel axles through the medium of rocking levers and valve stems as to admit steam to the cylinder at the beginning of the stroke and allow it to escape after the stroke is completed. Figure 26 shows a section through the center of one of these piston valves. It will be noticed that the live steam is admitted around a central portion of the valve, and that the steam escapes through the exhaust passages at each end of the piston valve. This type of valve is advantageous with high steam pressures for the reason that its blast, i.e., the steam pressure, does not press it against its bearings as is the case with the old type of slide valve, the wear of which with modern high steam pressures would be excessive, although under more recent slide valve design this objection does not hold. Figure 27. 295. Compound locomotives with tandem cylinders. The tandem compound locomotive, as recently built, is a locomotive in which the high-pressure cylinder is placed immediately in front of the low-pressure cylinder and in line with it. In the Vauquelin type it is necessary to have a piston rod for each of the two cylinders, one above the other, each taking hold of the same crosshead. In the tandem arrangement with the two cylinders each in line, but one piston rod is required. An example of a locomotive with this tandem arrangement of compound cylinders will be shown farther on. Figure 28. Figures 27 and 28 show two sections, one transverse and one longitudinal, of a type of large firebox boiler built by the American Locomotive Works at Schenectady. The diameter of the barrel of the boiler in front of the firebox is about 5 feet 8 inches, while the clear greatest width of the firebox is 5 feet 4.5 inches. The length of the latter is 8 feet 7 inches, making a total grate area in this particular instance of over 45 square feet. There are 338 2-inch tubes, each 16 feet in length. The total length over all of the boiler is 31 feet half an inch. The result of such a design is an arrangement by which a large grate area is secured and a corresponding high rate of combustion without a too violent draft. In designing locomotive boilers for bituminous coal 1 square foot of grate area is sometimes provided for each 60 to 70 square feet of heating surface in the tubes. Figure 29. 296. Evaporative efficiency of different rates of combustion. In the development of this particular class of locomotive boilers it is to be remembered that as a rule the highest rates of combustion frequently mean a decreased evaporation of water at boiler pressure per pound of fuel. Modern locomotives may burn over 200 pounds of coal per square foot of grate area per hour, and in doing so the evaporation may be less than 5 pounds of water per pound of fuel. On the other hand, when the coal burned does not exceed 50 pounds per square foot of grate area per hour, as much as 8 pounds of water may be evaporated for each pound of coal. It is judicious, therefore, to have large grate area, other things being equal, in order that the highest attainable efficiency in evaporation may be reached. 296a. Tractive force of a locomotive. The tractive force of a locomotive arises from the fact that one solid body cannot be moved over another, however smooth the surface of contact may be, without developing the force called resistance of friction. This resistance is measured by what is called the coefficient of friction, determined only by experiment. The resistance of friction and this coefficient will depend both upon the degree of smoothness of the surface of contact and on its character. If surfaces are lubricated, as in the moving parts of machinery, the force of friction is very much decreased, but in the absence of that lubricant it will have a much higher value. The coefficient of friction is a ratio which denotes the part of the weight of the body moved which must be applied as a force to that body in order to put it in motion against the resistance of friction. In the case of lubricated surfaces this ratio may be as small as a few hundredths. In the case of locomotive driving wheels and the track on which they rest this value is usually taken at 0.2 to 0.25. There are times when it is desirable to increase the resistance of friction between locomotive drivers and the rails. For this purpose a simple device, called the sandbox, is frequently placed on the top of a locomotive boiler with pipes running down from it so as to discharge the sand on the rails immediately in front of the drivers. The sand is crushed under the wheels and offers an increased resistance to their slipping. The tractive force of a locomotive may also be computed from the pressure of steam against the pistons in the steam cylinders. If the indicated horsepower in the cylinder be represented by HP, and if all frictional or other resistance between the cylinder and the drawbar be neglected, the following equality will hold: drawbar pull times speed of train in miles equals HP times 33,000 times 60 per hour times 5,280 if S equals speed in miles per hour, and if T equals drawbar pull, then the preceding equality gives T equals 375 times HPS. This value of the pull must be diminished by the friction of the locomotive as a machine, by the rolling resistance of the trucks and tender, and by the atmospheric resistance of the locomotive as the head of the train. Professor Goss proposes the following approximate values for these resistances in a paper read before the New England Railroad Club in December, 1901. A number of tests have shown that a steam pressure of 3.8 pounds per square inch on the piston is required to overcome the machine friction of the locomotive. Hence, if D is the diameter of the piston in inches, L the piston stroke in feet, and D the diameter of driver in feet, while F is that part of the drawbar pull required to overcome machine friction, the following equation will hold: F dot pi D equals 3.8 pi D superscript 2 times 2L times 2. For therefore F equals 3.8 D superscript 2L. D again, if W be the rolling load in tons on tender and trucks, excluding that on drivers, and if R be that part of the drawbar pull required to overcome the rolling resistance due to W, then experience indicates that approximately, in pounds, R equals 2 plus S, W 6 as before, S is the speed in miles per hour. Finally, if H be that part of the drawbar pull in pounds required to overcome the head resistance, atmospheric, of the locomotive, there may be written approximately H equals 0.11 S superscript 2. The actual drawbar pull in pounds available for moving the train will then be T equals T F or H equals 375 HP 3.8 D superscript 2 L W 2 plus S 0.11 S superscript 2. SD6. The maximum value of T should be taken as 1/4 the greatest weight on drivers. If H is the total heating surface in square feet, and if 12 pounds of water be evaporated per square foot per hour, while 28 pounds of steam are required per horsepower per hour, then HP equals 12H and 375 HP equals 161H. 28 SS. Hence T equals 161H 3.8 D superscript 2 L W 2 plus S 0.11 S superscript 2. SD6. The actual drawbar pull in pounds may then be computed by this formula. Some recent tests of actual trains, both heavy and light, on the NYC and HRRR between Mott Haven Junction and the Grand Central Station, New York City, a distance of 5.3 miles, by M. by J. Arnold, by means of a dynamometer car, gave the actual average drawbar pull per ton of 2,000 pounds as ranging from 12 to 25 pounds going in one direction and 12.1 to 24 pounds in the opposite direction. There were 8 tests in each direction, and the greatest speed did not exceed 30 miles per hour. As the diameter of the driver appears in the preceding formulae, it may be well to state that an approximate rule for that diameter is to make it as many inches as the desired maximum speed in miles per hour, i.e., 70 inches for 70 miles, or 80 inches for 80 miles, per hour. 297. Central Atlantic type of locomotive. Figure 29 represents what is termed the Central Atlantic type, single cylinder, of engine, which is used for hauling most of the fast passenger trains on the New York Central and Hudson River Railroad. The characteristics of boiler and firebox are such as are shown in figures 27 and 28. The cylinders are 21 inches internal diameter, and the stroke is 26 inches. The total grate area is 50 square feet, and the total heating surface 3,500 square feet. The total weight of the locomotive is 176,000 pounds, with 95,000 on the drivers. It will be observed that the total weight of locomotive per square foot of heating surface is scarcely more than 650 pounds, which is a low value. The boiler pressure carried may be 200 pounds per square inch or more. The tractive force of this locomotive may be taken at 24,700 pounds. There is supplied to these engines, among others, what is called a traction increasing device. This traction increaser is nothing more nor less than a compressed air cylinder secured to the boiler, so that as its piston is pressed outward, i.e., downward, it carries with it a lever, the fulcrum of which is on the equalizing lever of the locomotive frame, the other or short end of the lever being attached to the main bar of the frame itself. This operation redistributes the boiler load on the frame, so as to increase that portion which is carried by the drivers. This has been found to be a convenient device in starting trains and on upgrades. In the present instance, the traction increaser may be operated so as to increase the load on the drivers by about 12,000 pounds. It is not supposed to be used except when needed under the circumstances indicated. Figure 30. A number of indicator cards taken from the steam cylinders of these engines hauling the Empire State Express and other fast passenger trains on the Hudson River Division of the NYC and HRRR show that with a train weighing about 208 tons while running at a speed of 75 miles per hour 1323 HP was developed. Figure 30 shows these indicator diagrams. With a train weighing 685 tons 1452 HP was indicated at a speed of 63 miles per hour. 298, Consolidation Engine, NYC and HRRR. One of the heaviest wide firebox compound consolidation engines recently built for the New York Central Freight Service is shown in Figure 31. It will be noticed that there is but one cylinder on each side of the locomotive, and that they are of different diameters. One of these cylinders, 23 inches inside diameter, is a high-pressure cylinder, and the other, 35 inches inside diameter, is a low-pressure cylinder, the stroke in each case being 34 inches. The total grade area is 50.3 square feet, the firebox being 8 feet long by 6 feet 3 inches wide. The total heating surface is 3,480 square feet. The diameter of the barrel of the boiler at the front end is 72 inches. And the diameter of the driver 63 inches. The pressure of steam in the boiler is 210 pounds per square inch. The total weight of the locomotive is 194,000 pounds, of which 167,000 rests upon the drivers. These engines afford a maximum tractive force of 37,900 pounds. This engine is typical of those used for the New York Central Freight Service. They have hauled trains weighing nearly 2,200 tons over the New York Central Road. Figure 31. 299, P, B and LE Consolidation. The consolidation locomotive shown in Figure 32 is a remarkable one in that it was for a time the heaviest constructed, but its weight has since been exceeded by at least two of the decapod type built for the Santa Fe Company. It was built at the Pittsburgh Works of the American Locomotive Company for the Pittsburgh, Bessemer, and Lake Erie Railroad to haul heavy trains of iron ore. The total weight is 250,300 pounds, of which the remarkable proportion of 225,200 is carried by the drivers. The tender carries 7,500 gallons of water, and the weight of it when loaded is 141,100 pounds, so that the total weight of engine and tender is 391,400 pounds. The average weight of engine and tender therefore approaches 7,000 pounds per lineal foot. This is not a compound locomotive, but each cylinder has 24 inches inside diameter and 32 inches stroke, the diameter of the driving wheels being 54 inches. The boiler carries a pressure of 220 pounds, and the tractive force of the locomotive is 63,000 pounds. Figure 32. A noticeable feature of this design, and one which does not agree with modern views prompting the design of wide fireboxes, is its great length of 11 feet and its small width of 3 feet 4¼ inches. There are in the boiler 406 2¼ inch tubes, each 15 feet long, the total heating surface being 3,805 square feet. 300 LS and MS fast passenger engine. The locomotive shown in Figure 33 is also a remarkable one in some of its features, chief among which is the 19 feet length of tubes. It was built at the Brooks Works of the American Locomotive Company for the Lake Shore and Michigan Southern Railroad. The total weight of engine is 174,500 pounds, of which 130,000 pounds rests upon the drivers. The rear truck carries 23,000 pounds and the front truck 21,500 pounds. This is not a compound engine. The cylinders have each an inside diameter of 20½ inches, and 28 inches stroke. As this locomotive is for fast passenger traffic, the driving wheels are each 80 inches in diameter, and the driving wheel base is 14 feet. The firebox is 85 by 84 inches, giving a great area of 48.5 square feet and a total heating surface of 3,343 square feet. There are 285 2¼ inch flues, each 19 feet long. The tender carries 6,000 gallons of water. Cast and compressed steel were used in this design to the greatest possible extent, and the result is shown in that the weight divided by the square feet of heating surface is 52.18 pounds. Figure 33. 301, Northern Pacific Tandem Compound Locomotive. The diagram shown in Figure 34 exhibits the outlines and main features of a tandem compound locomotive to which allusion has already been made. It was built at Schenectady, New York, in 1900, for the Northern Pacific Railroad, and was intended for heavy service on the mining portions of that line. The diameters of the high and low pressure cylinders are respectively each 15 and 28 inches, with a stroke of 34 inches, while the boiler pressure is 225 pounds per square inch. The total weight of the machine is 195,000 pounds and the weight on the drivers 170,000 pounds, the diameter of the drivers being 55 inches. As the figure shows, it belongs to the consolidation type. The firebox is 10 feet long by 3.5 feet wide, giving a great area of 35 square feet, with which is found a total heating surface of 3,080 square feet. There are 388 2-inch tubes, each 14 feet 2 inches long. These engines are among the earliest compound tandem type and have been very successful. Other locomotives of practically the same general type have been fitted with a wide firebox, 8 feet 4 inches long by 6 feet 3 inches wide, with the great area thus increased to 52.3 square feet. Figure 34. 302, Union Pacific Vauquelin Compound Locomotive. The next example of modern locomotive is the Vauquelin compound type used on the Union Pacific Railroad. It is a 10-wheel passenger engine and one of a large number in use. The weight on the drivers is 142,000 pounds, and the total weight of the locomotive is about 185,000 pounds. The high-pressure cylinder has an inside diameter of 15.5 inches, while the low-pressure cylinder has a diameter of 26 inches. The stroke is 28 inches and the diameter of the driving wheel 79 inches. On the Union Pacific Railroad, the diameter of the driving wheel varies somewhat with the grades of the divisions on which the engines run. Figure 35. In some portions of the country, as in Southern California, oil has come into quite extended use for locomotive fuel. 303, Southern Pacific Mogul with Vanderbilt Boilered. The locomotive shown in Figure 36 belongs to the Mogul type, having 3 pairs of driving wheels and 1 pair of pilots. It is fitted with the Vanderbilt boiler adapted to the use of oil fuel. The locomotives of which this is an example were built for the Southern Pacific Company, and they have performed their work in a highly satisfactory manner. They are not particularly large locomotives as those matters go at the present day, as they carry about 135,000 pounds on the drivers and 22,000 pounds on the truck, giving a total weight of 157,000 pounds. The characteristic feature of the machine is its adaptation to the burning of oil, which requires practically no labor in firing, although the services of a fireman must still be retained. Figure 36. 304, the Sioux Decapod Locomotive. It has been seen that the results of Trevithick's early efforts was a crude and simple machine, with what might be termed, in courtesy to that early attempt, a single pair of drivers. Subsequently, as locomotive evolution took place, 2 pairs of drivers coupled with the horizontal connecting rod were employed. Then the mogul with the 3 pairs of coupled drivers was used, and at or about the same time the consolidation type with 4 pairs of coupled drivers was found adapted in a high degree to the hauling of great freight trains. The last evolution in driving wheel arrangement is exhibited in Figure 37. It belongs to what is called the decapod type. As a matter of fact, 5 pairs of coupled driving wheels have been occasionally used for a considerable number of years, but this engine is the decapod brought up to the highest point of modern excellence. As shown, it uses steam by the Vauquelin compound system, the small or high-pressure cylinder being underneath the low-pressure cylinder. They have been built by the Baldwin Locomotive Works for the Minneapolis, St. Paul, and Sault Ste. Marie Railroad Company, on what is called the Sioux Line. It has given so much satisfaction that more of this type but of greater weight are being built for the same company. This engine was limited to a total weight of 215,000 pounds, with 190,000 pounds on the drivers. Figure 37. Figure 38. Figure 39. Figure 40. 305, the A, T and SF decapod, the heaviest locomotive yet built. The heaviest locomotive yet constructed, consequently occupying the primacy in weight, is that shown in Figure 38. It is a decapod operated with others of its type by the A, T and SF company near Bakersfield, California. It is a tandem compound coal burner, as shown by the illustration, the high-pressure cylinder being in front of the low-pressure. The dimensions of cylinders are 19 and 32 by 32 inches stroke, and the driving wheels are 57 inches in diameter. The total height from the top of stack down to the rail is 15 feet 6 inches, while the height of the center of the boiler above the rails is 9 feet 10 inches. Figures 39 and 40 show some of the main boiler and firebox dimensions. There are 463 2¼ tubes, each 19 feet long. The total heating surface is 5,390 square feet, about 1/8 of an acre, the length of the firebox being 108 inches and the width 78 inches. The heating surface in the tubes is 5,156 square feet, and in the firebox 210.3 square feet, the grate surface having an area of 58.5 square feet. The boiler is designed to carry a working pressure of 225 pounds per square inch, the boiler plates being superscript 1/6 inch, /6 inch, and 7/8 inch thick, according to location. As shown by the illustrations, the boiler is what is termed an extended wagon top with wide firebox. The total weight of the locomotive itself is 267,800 pounds, while the weight on the driving wheels is 237,800 pounds, making 47,560 pounds on each axle. The tractive force of this locomotive is estimated to be over 62,000 pounds. 306. Comparison of some of the heaviest locomotives in use. The following table gives a comparison of the heaviest locomotives thus far built, as taken from the Railroad Gazette for January 31, 1902, revised to September 1, 1902. Comparison of heaviest locomotives. Atchison, Topeka and Santa Fe. Pittsburgh, Bessemer and Lake Erie. Union Railroad. Name of builder Baldwin Pittsburgh. Pittsburgh size of cylinders 19 and 32 by 32 inches. 24 by 32 inches. 23 by 32 inches. Total weight 267,800 pounds, 250,300 pounds, 230,000 pounds. Weight on drivers 237,800 pounds, 225,200 pounds, 208,000 pounds. Driving wheels, diameter 57 inches. 54 inches. 54 inches. Heating surface 5,390 square feet, 3,805 square feet, 3,322 square feet. Grate area 58.5 square feet, 36.8 square feet, 33.5 square feet. Illinois Central. Lehigh Valley. Name of builder Brooks Baldwin. Size of cylinders 23 by 30 inches. 18 and 30 by 30 inches. Total weight 232,200 pounds, 225,082 pounds. Weight on drivers 193,200 pounds, 202,232 pounds. Driving wheels, diameter 57 inches. 55 inches. Heating surface 3,500 square feet, 4,104 square feet. Grade area 37.5 square feet, 90 square feet. These instances of modern locomotive construction are impressive, especially when considered in contrast with the type of engine in use not more than 50 years ago. They indicate an almost incredible advance in railroad transportation, and they account for the fact that a bushel of wheat can be brought overland at the present time from Chicago to New York City, a distance of 900 miles, for about 1/3 of the lowest charge for delivering a valise from the Grand Central Station in the city of New York to a residence within a mile of it. Part 5. The Nicaragua Route for a Ship Canal. 307. Feasibility of Nicaragua route. The feasibility of a ship canal between the two oceans across Nicaragua has been recognized almost since the discovery of Lake Nicaragua in 1522 by Gil González de Avila, who was sent out from Spain to succeed Balboa, after the execution of the latter by Pedro Arias de Avila at Acla on the Isthmus of Panama. 308. Discovery of Lake Nicaragua. Gil González set sail from the Bay of Panama in January of that year northward along the Pacific coast as far as the Gulf of Fonseca. He landed there and proceeded to explore the country with 100 men, and found what he considered a great inland sea, as we now know, about 14 miles from the Pacific Ocean at the place of least separation. The country was inhabited, and he found a native chief called Nicareo, who was settled with his people at or near the site of the present city of Rivas. As he found it a goodly country, fertile and abounding in precious metals, he immediately proceeded to take possession of it for his sovereign, but the Spanish explorer was sufficiently gracious to the friendly chief to name Lake Nicaragua after him. From that time the part of Nicaragua in the vicinity of the lake received much attention, and the Spaniards made conquest of it without delay. Among those who were the earliest visitors was a Captain Diego Machuca, who, with 200 men under his command, explored Lake Nicaragua in 1529 and constructed boats on it, a brigantine among them. He seems to have been the first one who entered and sailed down the Desaguadero River, now called the San Juan, and one of the rapids in the upper portion of the river now bears his name. He pursued his course into the Caribbean Sea and sailed eastward to the Isthmus of Panama. Map of American Isthmus, showing proposed canal routes. 309. Early maritime commerce with Lake Nicaragua. Subsequently seagoing vessels passed through the San Juan River in both directions and maintained a maritime trade of some magnitude between the shores of Lake Nicaragua and Spain. Obviously these vessels must have been rather small for ocean-going craft, unless there was more water in the San Juan River in those early days than at present. There are some obscure traditions of earthquakes having disturbed the bed of the river and made its passage more difficult by reducing the depth of water in some of the rapids, but these reports are little more than traditionary and lack authoritative confirmation. It is certain, however, that the marine traffic, to which reference has been made, was maintained for a long period of years, its greatest activity existing at about the beginning of the 17th century. It was in connection with this traffic probably that the city of Granada at the northwestern extremity of the lake was established, perhaps before 1530. 310. Early examination of Nicaragua route. Although the apparently easy connection between the Caribbean Sea and Lake Nicaragua, together with the proximity of the latter to the Pacific coast, at once indicated the possibility of a feasible water communication between the two oceans, probably no systematic investigation to determine a definite canal line was made until that undertaken by Manuel Galisteo in 1779 under the instruction of Charles III, who was then on the throne of Spain. Galisteo made a report in 1781 that Lake Nicaragua was 134 feet higher than the Pacific Ocean, and that high mountains intervened between the lake and the ocean, making it impracticable to establish a water communication between the two. In spite of the discouragement of this report, a company was subsequently formed under the patronage of the Crown to construct a canal from Lake Nicaragua along the Sonoa River to the Gulf of Nicoya, but nothing ever came of the project. 311. English invasion of Nicaragua. The country was invaded in 1780 by an English expedition sent out from Jamaica under Captain Horatio Nelson, who subsequently became the Great Admiral. He proceeded up the San Juan River, and after some fighting captured by assault Fort San Juan at Castillo Viejo. Nelson and his force, however, were ill qualified to take care of themselves in that tropical country where drenching rains were constantly falling, and he was therefore obliged to abandon his plan of taking possession of Lake Nicaragua and returned instead to Jamaica. The tropical fevers induced by exposure reduced the crew of his own ship, 200 in number, to only 10 after his return to Jamaica, and he himself nearly lost his life by sickness. 312. Atlantic and Pacific Ship Canal Company. Subsequently to this period the Nicaragua route attracted more or less attention until Mr. E. G. Squire, the first consul for the United States in Nicaragua, negotiated a treaty between the two countries for facilitating the traffic from the Atlantic to the Pacific Ocean by means of a ship canal or railroad in the interest of the Atlantic and Pacific Ship Canal Company, composed of Cornelius Vanderbilt, Joseph L. White, Nathaniel Wolfe, and others. It was at this time that the Nicaragua route became prominent as a line of travel between New York and San Francisco. Ships carried passengers and freight from New York to Greytown, then transshipped them to river steamboats running up the San Juan River and across the southerly end of the lake to a small town called La Virgen, whence a good road for 14 miles overland led to the Pacific port of San Juan del Sur. Pacific Coast steamships completed the trip between the latter port and San Francisco. 313, Survey and Project of Colonel O.W. Childs. This traffic stimulated the old idea of a ship canal across the Central American Isthmus on the Nicaragua route to such an extent that Colonel O.W. Childs, an eminent civil engineer, was instructed by the American Atlantic and Pacific Ship Canal Company to make surveys and examinations for the project of a ship canal on that route. The results of his surveys, made in 1850–52, have become classic in interoceanic canal literature. He concluded that the most feasible route lay up the San Juan River from Greytown to Lake Nicaragua, across that lake, and down the general course of the Rio Grande on the west side of Nicaragua to Brito on the Pacific coast. This is practically identical with the route adopted by the Isthmian Canal Commission now, 1902, being discussed in Congress. 314. The project of the Maritime Canal Company. The project planned by Colonel Childs, like those which preceded it, had no substantial issue, but the general subject of an Isthmian canal across Nicaragua was, from that time, under almost constant agitation and consideration more or less active until the Maritime Canal Company of Nicaragua was organized in February, 1889, under concessions secured from the governments of Nicaragua and Costa Rica by Mr. A. G. Menecal. This company made a careful examination of all preceding proposed routes, and finally settled upon a plan radically different in some respects from any before considered. The Caribbean end of the canal was located on the Greytown Lagoon west of Greytown. From that point the line followed up the valley of the Desaada River and cut across the hills into the valley of the San Juan above its junction with the San Carlos. A dam was to be constructed across the San Juan River at Ochoa, below the mouth of the San Carlos, so as to bring the surface of Lake Nicaragua down to that point. From its junction with the San Juan River the canal line followed that river to the lake, across the latter to Los Lajes, and thence down the Rio Grande to the Pacific coast at Brito. It was contemplated under this plan to carry the lake level to a point called La Flor, 13.5 miles west of the lake, and drop down to the Pacific from that point by locks suitably located. After partially excavating the canal prism for about 3/4 of a mile from the Greytown Lagoon, constructing a line of railroad up the Desaada Valley, as well as a telegraph line, and doing certain other work preparatory to the actual work of construction, the Maritime Canal Company became involved in financial difficulties and suspended operations without again resuming them. Breakwater of the Maritime Canal Company. The closed former entrance to Greytown Harbor is shown on the left. 315. The work of the Ludlow and Nicaragua Canal Commissions. In 1895 and again in 1897 two commissions were appointed by the President of the United States to consider the plans and estimates of the Maritime Canal Company in the one case, and the problem of a ship canal on the Nicaragua route in the latter. Neither of these commissions, however, had the funds at its disposal requisite for a full and complete consideration of the problem. In 1899, therefore, the Isthmian Canal Commission was created by Act of Congress, and appointed by the President of the United States, to determine the most feasible and practical route across the Central American Isthmus for a canal, together with the cost of constructing it and placing it under the control, management, and ownership of the United States. This commission consisted of 9 members, and included civil and military engineers, an officer of the Navy, an ex-senator of the United States, and a statistician. It was the province and duty of this commission to make examinations of the entire isthmus from the Atrata River in the northwestern corner of South America to the western limits of Nicaragua for the purpose of determining the most feasible and practical route for a ship canal between those territorial limits. This brings the general consideration of the Isthmian Canal question to the Nicaragua route in particular, to which alone attention will be directed in this part. 316. The route of the Isthmian Canal Commission. The Isthmian Canal Commission adopted a route practically following the San Juan River from near Greytown to the lake, across the latter to Los Lajes on its westerly shore, and thence up the course of the Los Lajes River, across the Continental Divide into the Rio Grande Valley, and down the latter to Brito at the mouth of the Rio Grande on the Pacific coast. As has already been stated, this is practically the line adopted by Colonel Childs almost exactly 50 years ago. It is also essentially the route adopted by the Nicaragua Canal Commission appointed in 1897, and which completed its operations immediately prior to the creation of the Isthmian Canal Commission. The amount of work performed in the field under the direction of the Commission can be realized from the statement that 20 working parties were organized in Nicaragua with 159 civil engineers and other assistants, and 455 laborers. 317. Standard dimensions of canal prism. By the act of Congress creating it, the latter commission was instructed to consider plans and estimates for a canal of sufficient capacity to accommodate the largest ships afloat. In order to meet the requirements of those statutory instructions, the Commission decided to adopt 35 feet as the minimum depth of water in the canal throughout its entire length from the deep water of one ocean to that of the other, wherever the most feasible and practical route might be located, the investigations of the Commission having shown that the final location to be selected must narrow down to a choice between the Panama and the Nicaragua routes. It was further decided by the Commission that the standard width of excavation at the bottom of the canal should be 150 feet, with 500 feet for the ocean entrances to harbors, and 800 feet in those harbors. Greater widths than that of the bottom of standard excavations were also adopted for river and lake portions. The slopes of the sides of the excavation were determined to be 1 vertical on 1.5 horizontal for firm earth, but as flat as 1 vertical on 3 or even 6 horizontal for soft mud or silt in marshy locations. In rock cutting below water, the sides of the excavation would be vertical, but as steep as 4 vertical on 1 horizontal above water. Standard sections adopted by the Isthmian Canal Commission. The longest ship afloat at the present time, 1902, is the Oceanic of the White Star Line, and its length is about 704 feet. The widest ships, i.e., the ships having the greatest beam, are naval vessels, and at the present time none has a greater beam than about 77 feet. In order to afford accommodation for further development in both length and beam of ships without leading to extravagant dimensions, the Commission decided to provide locks having a usable length of 740 feet with a clear width of 84 feet. These general dimensions meet fully the requirements of the law, and were adopted for plans and estimates on both the Panama and Nicaragua routes. 318. The San Juan Delta. The entire Central American isthmus is volcanic in character, and this is particularly true of the country along the Nicaragua route with the exception of the lowlands immediately back of the ocean shore line in the vicinity of Greytown. From the latter point to Fort San Carlos, where the San Juan River leaves the lake, is approximately 100 miles. With the exception of the 15 miles nearest to the seacoast, the San Juan River runs mostly through a rugged country with high hills densely wooded on either side. The soil is mostly heavy clay, although the bottom of the valley immediately adjacent to the river is largely of sandy silt with some mixture of clay. Between the hills back of Greytown and the seacoast, the country is almost a continuous morass covered with coarse grasses and other dense tropical vegetation, but with a number of small isolated hills projecting up like islands in the surrounding marsh, and interspersed with numerous lagoons. All this flat country has the appearance of forming a delta through which a number of mouths of the San Juan River find their way. One of these, called the Lower San Juan, empties into the Greytown Lagoon, but the main mouth of the San Juan, called the Colorado, branches from the main river at the point where the Lower San Juan begins, about 13 or 14 miles from the ocean. The Colorado itself is composed of 2 branches, and at the place where it empties into the sea there are a number of long narrow lagoons parallel to the seashore, appearing to indicate comparatively recent shore formation. Again, a small river called the Rio San Juanillo leaves the main river 3 or 4 miles above the junction of the Lower San Juan and the Colorado, and pursues a meandering course through the low marshy grounds back of Greytown, and finally again joins the Lower San Juan near the town. This marshy lowland is underlaid by and formed largely of dark-colored sand brought down mostly from the volcanic mountains of Costa Rica by 2 rivers, the San Carlos and the Sarapiqui, the former joining the San Juan about 44 miles and the latter about 23 miles from the sea. Greytown Lagoon, formerly Greytown Harbor, showing Greytown in the distance. 319. The San Carlos and Sarapiqui Rivers. Both those Costa Rican rivers are subject to sudden and violent floods, and they bring down large quantities of this volcanic sand, the specific gravity of which is rather low. The San Carlos bears the greater burden of this kind. In fact, its bed, even when not in a state of flood, is at many points at least composed of moving sands. Both rivers are clear water streams except in high water stages. Below the junction of the San Carlos, the San Juan is necessarily in times of floods a large bearer of silt and sand, but above that point it carries little or no sediment. There are no streams of magnitude which join the San Juan between the lake and the San Carlos. 320. The Rapids and Castillo Viejo. About 54 miles from the ocean are the Machuca Rapids, and from that point to a distance of about 75 miles from the ocean other rapids are found, the principal of which are the Castillo and the Toro. The Castillo Rapids are at the point called Castillo Viejo, where there is located an old Spanish fort on the top of the high hill around the base of which the river flows. The town of Castillo Viejo has a small population of perhaps 500 to 600 people. It is a place with historical associations, to which reference has already been made. It was here that Captain, afterwards Admiral, Nelson captured the Spanish fort in 1780. It is a place of some importance in connection with the river traffic in consequence of necessary transshipment of freight and passengers to overcome the rapids. 321. The Upper San Juan. The upper reaches of the San Juan within about 20 miles of the lake are bordered with considerable marshy ground. In the vicinity of its exit from the lake there is a wide strip of soft marshy country around the entire southeastern shore. 322. The rainfall from Greytown to the lake. The entire country between Greytown and the lake is intensely tropical, and the vegetation is characteristically dense. It is particularly so at Greytown, where the total annual rainfall sometimes reaches as much as 300 inches. It rains many times in a day, and nearly every day in the year. The strong easterly and northeasterly trade winds, heavy laden with the evaporation from the tropical sea, meet the high ground in the vicinity of Greytown and precipitate their watery contents in frequent and heavy showers. The general course of the San Juan Valley is a little north of west or south of east, and the trade winds appear to follow the course of the valley to the lake. The rainfall steadily decreases as the seashore is left behind, so that at Fort San Carlos, the point of exit of the river from the lake, the annual precipitation may vary from 75 to 100 inches. There is no so-called dry season between the lake and the Caribbean Sea, although at Fort San Carlos the rainfall is so small between the middle of December and the middle of May that that period may perhaps be considered, relatively speaking, a dry season. It is evident, therefore, that all the conditions are favorable to luxuriant tropical growths over this entire eastern portion of the canal route, and the coarse grasses, palms, and other tropical vegetation found in it are indescribably dense. The same general observation is applicable to the forest and undergrowth throughout the entire course of the river from Greytown to Fort San Carlos. All of the high ground is heavily timbered, with undergrowth so dense that no survey line can be run until it is first completely cut out. That observation holds with added force throughout the swampy country adjacent to the seashore. All the heavy forest growth carries dense vines and innumerable orchids, which so cover the trunks and branches of trees as in many places completely to obscure them. The Maritime Canal Company's canal cut leading out of Greytown Lagoon. 323. Lake surface elevation and slope of the river. The lake surface has an area of about 3,000 square miles and varies in elevation with the amount of rainfall in its basin from about 97 or 98 to perhaps 110 feet above the ocean. The average elevation can probably be taken at about 104 feet above the sea. The length of the lake is about 103 miles, with a greatest width of 45 miles. The area of its watershed is about 12,000 square miles. Inasmuch as the length of the San Juan River from the ocean to the lake is but a little more than 100 miles, its average fall is seen to be about 1 foot per mile. The greatest slope of the river surface is at Castillo Rapids, where it falls about 6 feet in 3/8 of a mile. At the Machuca Rapids it falls about 4 feet in 1 mile. From the foot of Machuca Rapids to the mouth of the San Carlos, a distance of a little over 15 miles, the surface of the river falls about 1 foot only. This pool, with practically no sensible current, is called agua muerte, or dead water. The relatively great depth of this pool shows conclusively that the upper San Juan, i.e., above the mouth of the San Carlos, carries no silt, otherwise the pool would be filled. In other words, that part of the San Juan River is not a sediment bearer. The slope of the river surface in the Toro Rapids, about 27 miles from the lake, gives a fall of 7^3 feet in 1 miles. 324. Discharges of the San Juan, San Carlos, and Sarapiquide. In times of heavy floods the San Carlos River may discharge as much as 100,000 cubic feet per second into the San Juan, but such floods have a duration of a comparatively few hours only. Its low water discharge may fall below 3,000 cubic feet per second. The maximum outflow of the lake during a rainy season or a season of heavy rainfall probably never exceeds about 70,000 cubic feet per second, but that rate of discharge may continue for a number of weeks. The low water discharge of the San Juan above the mouth of the San Carlos may fall below 10,000 feet per second, or 13,000 feet per second below the mouth of the San Carlos but above that of the Sarapiquide. 325. Navigation on the San Juan. From what has been said of the San Juan River, it is evident that in times of low water no boats drawing more than about 5 or 6 feet can navigate it, and most of the river boats draw less than that amount. In times of low water no boat can navigate the lower San Juan drawing more than about 2.5 to 3 feet of water. Nor, again, can the ordinary river boats pass up the rapids at Castillo except at high water. It is necessary, therefore, that the larger boats used on the river confine their trips on the one hand between the mouth of the Colorado and Castillo, and on the other between Castillo above the rapids to Fort San Carlos. It is the custom, therefore, to transfer passengers and freight from boats below the rapids at Castillo by a short tramway to other boats in waiting above the rapids at that point. Boats pass up Machuca and Toro Rapids at practically all seasons, but sometimes with difficulty. In order to meet the exigencies of low water in the lower San Juan, a railroad called the Silico Lake Railroad, with 3 feet gauge, has been constructed from a point opposite the mouth of the Colorado, called Boca Colorado, to Lake Silico in the marshes back of Greytown, a distance of about 6 miles. Light draft boats connect Lake Silico with Greytown for the transfer of passengers and freight. The type of light draft steamboat used on the San Juan River is the sternwheel pattern, so much used on the western rivers of this country, the lower deck carrying the engines and boilers as well as freight, while the upper deck, fitted with crude staterooms, furnishes a kind of accommodation for passengers. 326. The canal line through the lake and across the west side. The little town of Fort San Carlos on a point raised somewhat above the lake where the San Juan River leaves the latter is the second place on the entire river from Greytown where any population may said to be found, and probably not more than 400 or 500 people even there. Its position is on the north side of the river, at the extreme southeastern end of the lake, commanding a fine view of the water and the country bordering it in that vicinity. To the westward lie the Salentiname Islands, a group a short distance to the north of which the sailing line for the canal in the lake is located. After passing this group of islands, that line deflects a little toward the south, so that its course westward is but a little north of west, straight to a point near to and opposite Los Lodges on the westerly shore of the lake, southwest from the large island on which Ontip and Madeira are located. Indeed, those two volcanic cones, the former still active, constitute the entire island. The point called Los Lodges is at the mouth of a small river of that name which discharges any sensible amount of water only during the wet season. It is located not more than 10 miles from Ontip, and affords a most impressive view of that perfect volcanic cone rising almost an exact mile above the water. The general direction of the canal route is a little west of south from Los Lodges on the lake to Brito on the ocean shore. The line follows the Los Lodges about 1.5 miles only of the 5 miles from the lake in a southwesterly direction to the point where the continental divide is crossed. The elevation of the divide at this place is about 145 feet only above sea level. The line then descends immediately into the valley of the Rio Grande and follows that stream to its mouth at Brito. The Maritime Canal Company's railroad near Greytown. 327. Character of the country west of the lake. The country on the west side of the lake exhibits a character radically different from that on the easterly side, i.e., between the lake and the Caribbean. It is a country in which much more population is found. While there are no towns along the 17 miles of the route from Los Lajes to Brito, the old city Rivas, containing perhaps 12,000 to 15,000 people, is about 6 miles from Los Lajes, and the small towns of San Jorge, Buenos Aires, Potosí, as well as others, are in the same general vicinity. Plantations of cacao and various tropical fruits abound, and there is a large amount of land under cultivation. It is largely a cleared country, so that far less dense forest areas are found. There are 2 distinct seasons in the year, the wet and the dry, the latter extending from about the middle of December to the middle of May. The annual rainfall is extremely variable, but in the vicinity of Rivas it may run from 30 or 40 to nearly 100 inches. The country is of great natural beauty, and one which, under well-administered governmental control, would afford many places of delightful residence. The trade winds blow across the lake from east to west with considerable intensity and great regularity. They produce a beneficial effect upon the climate and render atmospheric conditions far more agreeable than in that part of Nicaragua in the vicinity of Greytown. It will be remembered that Rivas is the city where the American filibuster Walker was taken prisoner by the Costa Ricans and Nicaraguans and shot in 1857. 328, Granada to Managua, thence to Corinto. At the northwestern end of the lake is located the attractive city Granada, sometimes called the Boston of Nicaragua. A reference to a map of Nicaragua will show that a short distance north of Granada is the river Tipitapa, which connects Lake Nicaragua with Lake Managua, the latter lying 18 miles to the northwest of the former. A railroad connects Granada with the city of Managua, which is the capital of Nicaragua, running on its way through the city of Masaya, chiefly noted for the volcano of the same name located nearby, and which has been subjected to a most destructive eruption. The old lava flow still shows its path of destruction by a broad black mark extending many miles across the country. A railroad connects Lake Managua at Mamatombo with the Pacific port of Corinto. 329, General features of the route. It is thus seen that the proposed route of the Nicaragua Canal lies first along the valley of the San Juan River, then across the lake, cutting the continental divide west of the latter at the low elevation of 145 feet above the sea, thence following the valley of the Rio Grande to the Pacific Ocean at Brito. From Greytown to Castillo, the San Juan River is the boundary between Nicaragua and Costa Rica, and concessions from both governments would be necessary for that part of its construction. From Castillo to the Pacific Ocean the route lies entirely in Nicaraguan territory, and the only concession necessary for that portion of the line would be from the government of Nicaragua. From Castillo to and around the southern end of the lake the boundary line is located 3 miles easterly from the river, following its turns, and the same distance from the lake shore, all by an agreement recently reached between the two governments. The summit level of the canal would therefore be the surface of the water in Lake Nicaragua, which is carried down to Conchita, 52 miles from the lake on the San Juan River toward the east, by a great dam located there, and to a lock between 4 and 5 miles from the lake toward the west. Hence the summit level would stretch throughout a distance of about 126 miles, leaving a little more than 46 miles on the Caribbean end and about 12 miles on the Pacific end of the regular canal section. The 50-mile stretch from the lake to the point where the canal cuts the San Juan River near Conchita is a canalized portion of the San Juan River, as a large amount of excavation must be done there in order to give the minimum required depth of 35 feet. The points of river bends or curves are in some cases cut off by excavated canal section in order to shorten the line and reduce the curvature. Considerable portions of the line in the lake, particularly near Fort San Carlos, would be excavated. For several miles in the latter vicinity large quantities of silt and mud must be removed, as the lake is shallow and the bottom is very soft. The entrance into the western portion of the canal at Los Lajes requires a large amount of rock excavation, as the shore and bed of the lake there are almost entirely of rock. Seen on the San Juan River. 330, Artificial Harbor at Greytown. The preceding observations are mostly of a general character, and give but little consideration to the engineering features of the canal construction. In considering the canal as a carrier of ocean traffic, probably the first inquiry will be that relating to harbors. In reality there is no natural harbor at either end of the Nicaragua route. 50 years ago there was an excellent harbor at Greytown into which ships drawing as much as 30 feet found ready entrance, and within which was afforded a well-protected anchorage. As early as that date, however, a point of land or sand pit was already pushing its way northward in consequence of the movement of the sand along the beach in that direction, and in 1865 it had nearly closed the entrance to the harbor. For many years that entrance has been entirely closed, and now what was once the protected harbor of Greytown is a shallow body of water, completely closed, and known as the Greytown Lagoon. There is a narrow, circuitous, and shallow channel leading from it out to an opening in the sandbar, which may be navigated by boats drawing not more than 2 or 3 feet, and by means of which freight and passengers are taken from steamers, which are obliged to anchor in the offing. Occasionally heavy storms break through this strip of sand between Greytown Lagoon and the ocean, and for a short time form a shallow entrance to the former. The sand movement in that vicinity northward or westward is so active that it is but a short time before such openings are again closed. The deepest water in the lagoon probably does not exceed 8 or 10 feet at the present time, and the most of it is much shallower. The tidal action at Greytown is almost nothing, as the range of tide between high and low is less than 1 foot. The mean level of the Caribbean Sea is the same as that of the Pacific Ocean. Under these circumstances it is necessary to create what is practically a new harbor at Greytown, and that work is contemplated in the plans of the Isthmian Canal Commission. The canal line is found entering the lagoon about 1 mile northwest of Greytown, where a harbor is planned having a length of 2,500 feet and a width of 500 feet, increased at the inner end to 800 feet to provide a turning basin. The entrance to this harbor from the ocean will be dredged to a width of 500 feet at the bottom, and it will be protected outside of the beach line by 2 jetties, the easterly about 3,000 feet long, and the westerly somewhat shorter. These jetties would be built of loose stone of irregular shape and size, resting on a suitable foundation, the largest, constituting the covering, weighing not less than 10 to 15 tons each. These jetties would be carried 6 feet above high water and have a top width of 20 feet. The trade winds, which blow from the easterly and northeasterly, would have a direction approximately at right angles to that of the easterly jetty, and ships making the entrance of the canal would consequently be protected against them while between the jetties. The easterly of these jetties would act as an obstruction against the westerly movement of the sand, but it is practically certain that a considerable amount of the latter would be swept into the channel, and possibly to some extent into the harbor, necessitating dredging a considerable portion of the time. The Commission estimates that the maintenance of the entrance and harbor would require an annual expenditure of $100,000. 331. Artificial harbor at Brito. The harbor at Brito presents a problem of a different kind. There is absolutely no semblance of a harbor there at the present time, 1902. It is simply a location on the sandy beach of the ocean protected against swells from the west by a projecting rocky point called Brito Head, the Rio Grande River emptying into the ocean just at the foot of Brito Head, between it and the canal terminus. The entire harbor and its entrance would be excavated in the low ground of that vicinity, composed mostly of sand and silt, although there would be a little rock excavation. The entrance to the harbor would be dredged 500 feet wide at the bottom, and be protected by a single jetty on the southeasterly side. The harbor itself would be excavated back of the present beach. It would have a length of 2,200 feet and a width of 800 feet. As the depth of water increases rather rapidly offshore, the 10-fathom curve is found at about 2,200 feet from low water mark, hence the jetty would not need to be more than probably 1,800 to 2,000 feet long. In this vicinity the water is usually smooth, indeed but few storms annually visit this part of the coast. The conditions are quite similar to those found on the coast of Southern California. There is little sand movement in this vicinity, and the annual expenditures for maintenance of the harbor and entrance would be relatively small. The Commission has estimated them at $50,000. 332. From Greytown Harbor to Lock No. 2. The canal line, on leaving the harbor at Greytown, is found in low marshy ground for a distance of about 7 miles. The excavation being mainly through the sand, silt, mud, and vegetable matter characteristic of that location. Throughout almost this entire distance the natural surface is but little above sea level. The first ground elevated much above this marshy country is known as the Misterioso Hills, in which lock number 1 is founded, having a lift of 36.5 feet and raising the water surface in the canal by that amount above sea level. Another stretch of marshy country, but not quite so wet as the preceding, follows for a distance of about 11 miles, when the Rio Negro hills rise abruptly to an elevation of a little over 150 feet above sea level. At this point is located lock number 2, with a lift of 18.5 feet. This lock is about 21 miles from the 6-fathom line off Greytown. The canal line here practically reaches the San Juan River, the latter lying a considerable distance easterly of the canal, between this point and the ocean. Between Greytown and lock number 2 embankments, never reaching a greater height than 10 to 15 feet, are required to keep the water in the canal at various locations along the low ground. These embankments do not necessarily follow parallel to the center line of the canal route, but are planned to connect hills, or rather high ground, so as to reduce their length and give them a more stable character than if they were located close to the canal excavation. While some embankments will still be found above lock number 2, they are few, and even lower than those already noticed. From lock number 2 to Lake Nicaragua, the route of the canal lies practically along the San Juan River, the chief exception to that statement being the cutoff in the vicinity of the Conchita Dam. Lock number 1, Nicaragua route, about 7 miles from Greytown. Telegraph office at Ochoa on the San Juan River. 333, from lock number 2 to the lake. Inasmuch as both the Sarapiqui and San Carlos rivers flow from Costa Rican territory into the San Juan, that is, from its right bank, the canal line necessarily is located along the northerly or left bank of that river. At a distance of 23 miles from the ocean, the canal line cuts through what are called the Sarapiqui Hills opposite the mouth of the river of that name, and at a distance of a little over 26 miles from the ocean it pierces the Tamborcito Ridge, where is found the deepest cutting on the entire route. The total length of cut through this ridge is about 3,000 feet, but its greatest depth is 297 feet, and it consists largely of hard, basaltic rock. The next lock, or lock number 3, is found about 17 miles from lock number 2, or 38 miles from the sea, and it has, like lock number 2, a lift of 18.5 feet, raising the surface of the water in the canal to an elevation of 73.5 feet above the sea. Continuous heavy cutting through what are called the Machado Hills brings the line to lock number 4, at a distance of a little less than 41 miles from the ocean. This lock has a lift varying from 30.5 to 36.5 feet, inasmuch as it raises the surface of the water in the canal to the summit level in the lake. The maximum lift of 36.5 feet would be required when the lake level stands at an elevation of 110 feet above the sea, and 30.5 feet when the same surface stands at an elevation of 104 feet above the sea. Although the water surface in the canal level above this lock is identical with the summit level in the lake, the canal line again runs through continuous heavy cutting for a distance of 5 miles before it reaches the canalized San Juan. This portion of the line between lock number 4 and the San Juan River is called the Conchita Cutoff, for the reason that the point called Conchita, where the Great Dam is located, is but 3 miles down the river from the point where the canal enters it. From Conchita to the lake, as has already been stated, the canal line follows the course of the San Juan River, which must be canalized by considerable excavation of earth and rock, both along the bed and in cutoffs. The greater part of this cutting must obviously be on that portion of the river toward the lake, as that is the highest part of the river bed in its natural condition. 334, Fort San Carlos to Brito. The distance from the point of entrance of the canal into the San Juan River near Conchita to Fort San Carlos on the shore of Lake Nicaragua is about 50 miles, while the distance across the lake on the canal line is 70.5 miles, which brings the line to Los Lodges on the southwesterly shore of the lake. There is considerable heavy cutting through the continental divide between the lake and the first lock westerly of it, i.e., lock number 5. The maximum cutting is but 76 feet in depth, and the average is but little less than that for nearly 3 miles. This lock is located a little less than 10 miles from the lake and nearly 176 miles from the 6-fathom line off Greytown. The place at which this lock is located is known as Buen Retiro. The lift of lock number 5 varies from 28.5 feet as a maximum to the minimum of 22.5 feet, bringing the water surface in the canal down to 81.5 feet above mean ocean level. Lock number 6 is located but about 2 miles west of lock number 5, and also has a lift of 28.5 feet. The line now runs along the course of the Rio Grande to the ocean, lock number 7 being also 2 miles west of lock number 6, again with a lift of 28.5 feet. The last lock on the line, or lock number 8, but a mile from the Pacific Ocean, and about 182 miles from the Caribbean Sea, has a maximum lift of 28.5 feet, and a minimum lift of 20.5 feet, the range of tide in the Pacific Ocean being but 8 feet at Brito. There are thus 4 locks between the lake and the Pacific Ocean, each having a possible lift of 28.5 feet. Surveying party of the Isthmian Canal Commission on the San Juan River. The entire distance between the 6-fathom lines in the two oceans is 183.66 miles. 335. Examinations by borings. Obviously it is of the greatest importance that such structures as the locks and dams required in connection with this canal route should be founded on bedrock. In order to determine not only such questions, but the character of all materials to be excavated from one end of the route to the other, a great number of borings were made along the canal line, not only by the water jet process, but also with the diamond drill. By means of the latter, whenever it was so desired, cores or circular pieces could be taken out of the bedrock so as to show precisely its character at all depths. These borings, both through earthy material by the jet and into bedrock by the diamond drill, were made at suitable distances apart along the center line of the canal, and in considerable numbers, closer together at proposed lock and dam sites. By these means every lock on the line has certainly been located on bedrock, as well as the great dam at Conchita. In addition to this, the Commission has been able to classify the material to be excavated, so that if the canal should be built, every contractor would know precisely the character and quantity of the various materials which he would have to deal with. 336. Classification and estimate of quantities. The following table is arranged to exhibit a few only of the principal items of excavation, so as to give an approximate idea at least of the magnitude of the work to be done. Dredging 130,920,905 cu yards, dry earth 47,440,316, soft rock 14,029,170, hard rock 24,151,214, rock underwater 2,780,040. Embankment and backfilling 8,389,960, clearing 6,831 acres. Stone pitching 250,089 square yards, concrete, excluding retaining walls 3,400,840 cu yards, concrete in retaining walls 424,321, cut stone 22,272, steel and iron, excluding cast iron culvert lining 61,735,230 pounds. Cast iron culvert lining 19,286,000, brick culvert lining 34,542 cu yards, cost of lock machinery $1,600,000, excavation in cofferdam 9,907 cu yards, pneumatic work 145,557, piling 415,600 lin, foot rock fill in jetties 451,500 cu yards, clay puddle, bottom and side 936,803.37. Classification and unit prices. The classification of the material to be excavated, both on the Nicaragua and Panama routes, was one to which the Commission gave very thoughtful study, no less than to the prices to be used in making the estimates. The following table, taken from pages 67 and 68 of the Commission's report, exhibits the classification and the prices adopted by the Commission for purposes of its estimates. Removal of hard rock, per cu yard $1.15, removal of soft rock, per CUYD .80, removal of earth, not handled by dredge, per cu yard 45, removal of dredgeable material, per cu yard 20, removal of rock underwater, per cu yard 4.75, embankments and backfilling, per cu yard 60, rock and jetty construction, per cu yard 2.50, stone pitching, including necessary backing, per square yard 2.00, clearing and grubbing in swamp sections of Nicaragua, per acre 200.00 other clearing and grubbing on both routes, per acre 100.00 concrete, in place, per cu yard 8.00 finished granite, per cu yard 60.00 brick in culvert lining, per cu yard 15.00 all metal and locks, exclusive of machinery and culvert linings, per pound. 0.75 all metal in sluices, per pound. 0.75 cast iron in culvert lining, per pound. 0.4 allowance for each lock chamber for operating machinery 50,000.00 additional allowance for each group of locks for power plant 100,000.00 price of timber and locks, per mbm 100.00 sheet piling in spillways, per mbm 75.00 bearing piles in spillways, per lin. Foot .50 average price of pneumatic work for the Bohio Dam, below elevation, 30, per cu yard 29.50 caisson work for the Conchita Dam, in place, per cu yard 20.00 single-track railroad complete with switches, stations, and rolling stock, per mile of main line 75,000.00. There are evidently other more or less uncertain expenditures, depending upon all possible conditions affecting the cost of such work, including those of climate, police, and sanitation. In order to cover such expenditure, the Commission determined to add 20% to all its estimates of cost on both routes, and that percentage was so added in all cases. 338. Curvature of the route. Among the engineering features of a ship canal line, it is evident that curvature is one of great importance. Small steam vessels may easily navigate almost any tortuous channel, but it is not so with great ocean steamships. On the other hand, it may require very deep and expensive cutting to reduce the curvature of the route, as curves are usually introduced to carry the line around some high ground. It is necessary, therefore, to make a careful and judicious balance between these opposing considerations. The Commission wisely decided to incur even heavy cutting at some points for the purpose of avoiding troublesome curvature on the Nicaragua route. The table on page 415, taken from page 135 of the Commission's report, gives all the elements of curvature for the entire line. Boring party of the Isthmian Canal Commission on a raft in the San Juan River. From the description of the line as given, it is evident that much curvature must be found in spite of the most judicious efforts to avoid it, and the table indicates that condition. Yet the amount of curvature may be considered moderate for a location through such a country as Nicaragua. The smallest radius is seen to be a little over 4,000 feet. The result may be considered satisfactory for such a difficult canal country, although the total amount of curvature is rather formidable. Number of curves. Radius. Length. Total degrees of curve. Feet. Miles. Degree 2 17,189 1.53 26 51 10 8 11,459 6.80 179 31 50 4 8,594 4.31 151 40 501 8,385 1.43 51 44 32 7,814 1.90 73 28 31 7,759 1.73 67 16 55 6,876 4.64204 34 402 5,927 2.40122 41 2016 5730 11.08584 47 402 5289 2.27129 45 501 5209 1.15 66 38 32 5056 1.22 73 17 41 4982.82 49 49 003 4911 2.75 169 36 001 4297.63 44 1951 4175.81 58 20 44 4045 3.82285 25 40 56 49.29 2339 50 30 339. The Conchita Dam and Wastewade. the most important single engineering feature of the whole plan is the dam at Conchita. The ordinary low water elevation in the river at the dam site may be taken at about 55 feet above the sea. Inasmuch as the greatest elevation of the water in the lake is supposed to be about 110 feet, it will be seen that its surface will be but 55 feet above the present elevation, making its maximum depth at that point about 105 feet if there should be no fill on the upstream side of the dam, inasmuch as the present depth of water in the river at the stage assumed is about 50 feet. This dam would be a structure of concrete masonry with cut stone facing only at a few points where it would be advisable to use that material. A large part of the flood discharge, or the discharge of other surplus water, would be made over a properly designed crest of the dam, hence its outline would be that shown in the accompanying figure, shaped so as to prevent the overflowing sheet of water from damaging the structure. This dam will be founded upon pneumatic caissons, and the borings made by the Commission show that the deepest of them would reach satisfactory bedrock at no greater depth than 25 feet below sea level, or about 80 feet below the ordinary stage of water in the river. The construction of this dam therefore would involve no unusual operations, but it would all be performed within the more usual and easy limits of the pneumatic process of constructing foundations. The masonry crest of this dam would be finished at the elevation of 97 feet above sea level, or about 13 feet below the highest elevation of water in the lake. The length of that part of this masonry dam, located on pneumatic caissons, would be 731 feet, but the total length of the entire masonry structure would be 1,310 feet. The total length of crest, including the masonry piers on it, over which the surplus waters would flow, would be 810 feet, but there are 20 piers 9 feet thick, so that the net length of crest available for overflow of waste waters would be about 630 feet. The piers to which reference is made are those required for the support of the movable gates of the stony type which would be employed to regulate the discharge over the dam. The maximum elevation of the tops of these piers required for the support and operation of the stony gates is 132 feet above sea level. The masonry dam thus furnished with movable gates can be used in times of flood to prevent the water of the lake rising above about 110 feet above sea level. In times of low rainfall or during the dry season, the gates would prevent the escape of water needed for storage. Castillo Viejo, on the San Juan River, about 37 miles from the lake and at the Castillo Rapids. The old fort is shown on the right at the summit of the hill. The total available length of crest on this masonry dam is not sufficient to exercise all the control that is needed to keep the lake within desired limits, and the Commission was obliged to avail itself of a low depression or saddle between the hills less than a half-mile easterly of the dam site. The depression affords an additional total length of crest of 1,239 feet, or, taking out 31 piers, each 9 feet wide, a net available length of 960 feet, making in combination with the crest of the main dam a total net available length of 1,590 feet. The total wastage over these two structures, i.e., the main dam at Conchita and the Conchita Wasteway on the Costa Rican side of the river, may be at the rate of 100,000 cubic feet per second, with a maximum depth over the crest of 7 feet, which is sufficient to meet the demands of the heaviest rainfall in the lake basin. The plans and elevations on pages 421, 423, and 424 show all the main features of both the Conchita Dam and Wasteway as designed by the Commission. 340. Regulation of the lake level. One of the most important engineering questions connected with the consideration of the Nicaragua route is that of the regulation or control of the surface of the water in Lake Nicaragua constituting the summit level of the canal. As has already been stated, the drainage basin of the lake, about 12,000 square miles in area, is subjected to an annual wet season extending from about the middle of May to the middle of December, the dry season extending over the remaining portion of the year. The average annual rainfall over the entire lake basin is not accurately known, although the Isthmian Canal Commission maintained rainfall records at several points on the lake shore and at other points in the basin during periods of 1.5 to 2 years, and records running back over periods of perhaps 12 to 15 years are available from Rivas, Granada, and Masaya. Fortunately, also, both the Nicaragua and the Isthmian Canal Commissions maintained gauging stations at various points on the San Juan throughout the periods of service of these commissions, so that the discharges of the river could be known from accurate measures at various seasons for at least 2 or 3 years. These observations, although not as extended as could be desired, yield sufficient data for a comparatively thorough treatment of the subject of lake surface control. Obviously, throughout the rainy season of the year, except during years of low rainfall, some water would necessarily be wasted from the lake because its retention would raise the surface of the lake too high, causing damage, floods, or injurious overflows at various places around the lake shore. On the other hand, unless some water were stored from the rainy periods or wet seasons, there would not be sufficient in the lake to supply during the dry period of the year, or during low rainfall years, the requisite quantity for the wastage of evaporation from its surface and for the operation of the canal, and at the same time maintain the minimum depth of water of 35 feet required in the canal. It was necessary, therefore, to design at least the general features of such regulating works as would prevent the lake from rising too high in wet periods, and from falling too low in dry periods or low rainfall years. Village of Fort San Carlos at entrance to the San Juan River. Lake Nicaragua is on the right and San Juan River in the middle ground. 341. Evaporation and lockage. The observations of both commissions show conclusively that the average evaporation from the surface of Lake Nicaragua is about 60 inches or 5 feet per year, varying from perhaps a maximum of 6 inches per month to a minimum of possibly about 4 inches per month. Furthermore, careful estimates of the quantity of water required for the purposes of the canal, on the supposition that about 10 million tons of traffic would pass through it annually, including lockage, leakage through the gates of the locks, evaporation, power purposes, and other incidentals, show that about 1,000 cubic feet of water per second must be provided. Whatever may be the character of the season, therefore, there must be at least sufficient water stored in the lake to provide for the wastage of evaporation from the lake and canal surfaces and for the proper operation of all the locks throughout the length of the canal. The superficial area of Lake Nicaragua is but little less than 3,000 square miles. The quantity of water required for the operation of the canal, amounting to 1,000 cubic feet per second, would, for the entire year, make a layer of water over the lake surface of less than 5 inches in thickness. In other words, the operation of the canal, for a traffic of about 10 million tons annually, requires an amount of water less than 1/12 of that which would be evaporated from the lake surface during the same period. 342. The required slope of the canalized river surface. The dam located at Conchita and fitted with suitable movable gates affords means of accomplishing the entire lake surface control. That dam is located, however, nearly 53 miles from the lake, and in order that the requisite discharge may take place over it during the rainy season, there must be considerable slope of the water surface in the canalized river from the lake down to the dam. It was necessary, therefore, to compute that slope, from data secured by the Commission, with the lake surface at various elevations between the minimum and maximum permitted. These slopes were found to be such that the difference in elevations of the surface of the water at the dam and in the lake might vary from about 6 to 9 feet, those figures representing the total fall for the distance of 53 miles. 343. All surplus water to be discharged over the Conchita Dam. The Nicaragua Commission contemplated the construction of dams not only on the San Juan River at Boca San Carlos, about 6 miles below Conchita, but also another a few miles west of the lake at La Flor, so as to discharge the surplus waters at both points, but by far the largest part over the dam at Boca San Carlos. The Isthmian Canal Commission, however, decided to build no dam on the west side of the lake, but to discharge all the surplus waters over the dam at Conchita. The active volcano Ometepe in Lake Nicaragua, showing clouds on leeward side of the summit. The crater is nearly 11 miles from the canal line. 344. Control of the surface elevation of the lake. The rainfall records in the lake basin have shown that a dry season beginning as early as November may be followed by an extremely low rainfall period, which in turn would be followed by a dry season in natural sequence, lasting as late as June. It may happen, therefore, that from November until a year from the succeeding June, constituting a period of 19 months, there will be a very meager rainfall in the lake basin, during which the precipitation of the 7 low rainfall wet months may not be sufficient even to make good the depletion of evaporation alone during the same period. It would be necessary, then, at the end of any wet season whatever, i.e., during the first half of any December, or in November, to make sure of sufficient storage in the lake to meet the requirements of the driest 19 months that can be anticipated. That condition was assumed by the Commission, and the elements of control of the lake surface, in its plans, are such as to afford resources to meet precisely those low water conditions. Plan of Conchita Dam site, showing location of boring. The Commission's study of these features of the Nicaragua Canal problem resulted in plans of works to prevent the surface of the lake ever falling below 104 feet above sea level, or rarely if ever rising higher than the elevation of 110 feet above the same level, thus making the possible range of the lake surface about 6 feet between its lowest and its highest position. Obviously, at the end of a dry season the gates at the dam will always be found closed, and there will be no water escaping from the lake except by evaporation and to supply the needs of canal operation. It is equally evident that the gates will also remain closed so as to permit no wastage during the early part of the wet season. As the wet season proceeds, the surface of the lake will rise toward, and generally quite to its maximum elevation. The operation of wasting over the weirs will then commence. The time of beginning of this wastage will depend upon the amount and distribution of the rainfall during the wet period. Indeed, no wastage whatever would be permitted during such a low-water wet season as that shown by the records of 1890, which was almost phenomenal in its low precipitation. The rainfall for the entire drainage basin would be impounded in the lake in that case, and it would then fall short of restoring the depletion resulting from evaporation and requirements of the canal. On the other hand, during such a wet season as that of 1897, wastage would begin at an early date. In general, it may be said that neither the rate nor the law of the rise of water surface in the lake can be predicted. There will be years when no wastage will be permitted, but generally considerable wastage will be necessary in order to prevent the lake rising above the permissible highest stage. Profile of site of Conchita Dam showing borings. Detailed computations based upon the statistics of actual rainfall records in the basin of Lake Nicaragua may be found by referring to pages 147 to 152 of the report of the Isthmian Canal Commission, and they need not be repeated here. Those computations show among other things that October is often a month of excessive rainfall, and that the greatest elevation of the lake surface is likely to follow the precipitation of that month. Hence the greatest discharge of surplus waters over the Conchita Dam may be expected in consequence of the resulting runoff or inflow into the lake. Those computations also show that at long intervals of time the lake surface might reach an elevation of nearly 112 feet above sea level for short periods, causing the discharge in the canalized river or over the Conchita Dam to reach possibly 76,000 cubic feet per second, the elevation of the water at the dam being 104 feet above sea level. Furthermore, the Ceballos River and one or two other small streams, emptying into the San Juan above the dam, might concurrently be in flood for at least a few hours and augment the discharge over the dam to 100,000 cubic feet per second. The regulating works at the dam, consisting of the movable, stony, gates, were devised by the Commission to afford that rate of discharge, an aggregate net or available length of overflow crest at the dam and wasteway of 1,590 feet being necessary for that purpose, with a depth of water on the crest not exceeding 7 feet. Conchita Dam. Section showing caissons Conchita Dam. Diagram showing arrangement of sluice gate. The Commission states on page 156 of its report, while, therefore, no detailed instructions can be set forth regarding the condition of the sluices at the wasteway on specified dates, the general lines of their operation should be stated below, viz. 1. A full lake with surface probably a little above 110 feet on December 1st. 2. Wasteway sluices closed at least from about December 1st to some date in the early portion of the succeeding rainy season, or throughout that season if it be one of unusually low precipitation. 3. A variable opening of wasteway sluices, if necessary, during the intermediate portion of the rainy season, so as to maintain the lake surface elevation but little, if any, below 110 at the beginning of October. 4. The operation of wasteway sluices during October and November so as to reach the 1st of December with a full lake, or lake elevation probably a little above 110 feet. It is thus seen that while the measures for control and regulation are entirely feasible, they are not sharply defined, nor so simple that some experience in their operation might not be needful for the most satisfactory results. 345. Greatest velocities in canalized river. It is necessary to ascertain whether the velocities induced in the canalized portions of the San Juan River would not be too high for the convenience of traffic during the highest rainfall season. The following table and the succeeding paragraph, taken from the Commission's report, show that no sensible difficulty of this kind would exist. Elevation of lake. Elevation of water at dam. 103 feet. 104 feet. Feet. Feet per second. Miles per hour. Feet per second. Miles per hour. 110.4.162.83.92.7 111.4.513.14.22.9 112.4.853.34.53.1 The discharge of the river corresponding to the velocity of 2.7 miles per hour is 63,200 cubic feet per second, while that corresponding to 3.3 miles per hour is 77,000 cubic feet per second. These estimated high velocities will occur but rarely, and they will not sensibly inconvenience navigation. In reality they are too high, for the reason that while the overflow at the minimum river section materially increases the areas of those sections, it has been neglected in this discussion. Brito, at the Pacific terminus of the Nicaragua route, showing the mouth of the Rio Grande on the left and the easterly side of Brito Head. 346. Wasteways or overflows. At a number of places on the route there are some small streams which must be taken into the canal, and which when in flood require that certain wasteways or overflows from the canal prism should be provided at or near where such streams are received. These wasteways are simply overfall weirs with the crests at the elevation of the lowest water surface in the canal prism. The principal works of this kind are on the east side of the lake and involve a total drainage area or area of watershed of about 107 square miles. Ample provision has been made by the Commission for all such structural features. 347. Temporary harbors and service railroad. Before actual work could be begun at either end of the Nicaragua route, temporary harbors would have to be constructed both at Greytown and at Brito to enable contractors to land plant and supplies or other material. These temporary harbors would probably require no greater depth of water than 18 feet, but they would be works of considerable magnitude, and provision was made for them in the Commission's estimate of cost. Again, a service railroad of substantial character would have to be built from Greytown up to Ceballos, approximately halfway between the Conchita Dam and Fort San Carlos, as well as from the west shore of the lake to Brito, making a total line of about 100 miles. The Commission estimated the cost of this railroad and its rolling stock at $75,000 per mile. 348. Itemized statement of length and cost. The following table gives the lengths of the various portions of the canal and the principal items of its cost, so arranged as to show the classification of the various items of the total sum to be expended for all purposes during the construction of the entire work. The Commission estimated the total time required in preparing for and performing the actual construction of the work at 8 years, but the writer believes that at least 2 years more should be allowed for the work. Miles. Cost. Greytown Harbor and entrance $2.152,198,860 section from Greytown Harbor to Lock No. 1, including approach wall to Lock $7.444,899,887 diversion of Lower San Juan 40,100 diversion of San Juanillo 116,760 Lock No. 1. Including excavation $205,719,689 section from Lock No. 1 to Lock No. 2, including approach walls, embankments, and wasteway $10.966,296,632 Lock No. 2, including excavation $204,050,270 section from Lock No. 2 to Lock No. 3, including approach walls, embankments, and wasteway. $16.7519,330,654 Lock No. 3, including excavation $203,832,745 section from Lock No. 3 to Lock No. 4, including approach walls, embankments, and wasteway $2.774,310,580 Lock No. 4, including excavation. 205,655,871 section from Lock No. 4 to San Juan River, including approach wall and embankments. 5.308,579,431 Conchita Dam, including sluices and machinery. 4,017,650 auxiliary wasteway, including sluices, machinery, and approach channels. 2,045,322 San Juan River section. 49.64 23,155,670 Lake Nicaragua section. 70.517 877,611 Lake Nicaragua to Lock No. 5, including approach wall to lock and receiving basins for the Rio Grande and Choclatan. 9.09 19,566,575 diversion of the Los Lodges. 199,382 Lock No. 5, including excavation. 204,913,512 Dam near Buen Retiro. 125,591 section from Lock No. 5 to Lock No. 6, including approach walls and wasteway. 2.043,259,283 Lock No. 6, including excavation. 204,368,667 section from Lock No. 6 to Lock No. 7, including approach walls, embankments, and wasteway. 1.832,309,710 diversion of Rio Grande. 176,180 Lock No. 7, including excavation. 204,709,502 section from Lock No. 7 to Lock No. 8, including approach walls, embankments, and wasteway. 2.431,787,496 diversion of Rio Grande. 117,580 Lock No. 8, including excavation. 204,920,899 section from Lock No. 8 to Brito Harbor, including approach wall. 235,553,476 Brito Harbor and entrance, including jetty. 921,509,470 railroad, including branch line to Conca Dam site, at $75,000 per mile. 7,575,000 engineering, police, sanitation, and general contingencies, 20%, 1,644,010 aggregate. 183.66 $183,864,062. Part 6. The Panama Route for a Ship Canal. 349. The first Panama Transit Line. The Panama Route as a line of transit across the isthmus was established, as near as can be determined, between 1517 and 1520. The first settlement, at the site of the town of Old Panama, 6 or 7 miles easterly of the present city of that name, was begun in August, 1517. This was the Pacific end of the line. The Atlantic end was finally established in 1519 at Nombre de Dios, the more easterly port of Acla, where Balboa was tried and executed, having first been selected but subsequently rejected. The old town of Panama was made a city by royal decree from the throne of Spain in September, 1521. At the same time it was given a coat of arms and special privileges were conferred upon it. The course of travel then established ran by a road well known at the present time through a small place called Cruces on the river Chagres, about 17 miles distant from Panama. It must have been an excellent road for those days. Bridges were even laid across streams and the surface was paved, although probably rather crudely. According to some accounts it was only wide enough for use by beasts of burden, but some have stated that it was wide enough to enable 2 carts to pass each other. 350. Harbor of Portobello established in 1597. The harbor of the Atlantic terminus at Nombre de Dios did not prove entirely satisfactory, and Portobello, westerly of the former point, was made the Atlantic port in 1597 for this Isthmian line of transit. The harbor of Portobello is excellent, and the location was more healthful, although Portobello itself was subsequently abandoned, largely on account of its unhealthfulness. Profile of Panama Route. Profile of Nicaragua Route. Profiles of the 2 canal routes. The horizontal scales are different, but the vertical scales are the same. 351. First traffic along the Chagres River, and the importance of the Isthmian commerce. As early as 1534, or soon after that date, boats began to pass up and down the Chagres River between Cruces and its mouth on the Caribbean shore, and thence along the coast to Nombre de Dios and subsequently to Portobello. The importance of the commerce which sprang up across the isthmus and in connection with this Isthmian route is well set forth in the last paragraph on page 28 of the report of the Isthmian Canal Commission. The commerce of the isthmus increased during the century and Panama became a place of great mercantile importance, with a profitable trade extending to the Spice Islands and the Asiatic coast. It was at the height of its prosperity in 1585, and was called with good reason the tollgate between Western Europe and Eastern Asia. Meanwhile, the commerce whose tolls only brought such benefits to Panama enriched Spain, and her people were generously rewarded for the aid given by Ferdinand and Isabella in the effort to open a direct route westward to Cathay, notwithstanding the disadvantages of the Isthmian transit. 352. First survey for Isthmian Canal ordered in 1520. This commercial prosperity suggested to those interested in it, and soon after its beginning, the possibility of a ship canal to connect the waters of the two oceans. It is stated even that Charles V directed that a survey should be made for the purpose of determining the feasibility of such a work as early as 1520. The governor, Pascual de Goya, reported that such a work was impracticable and that no king, however powerful he might be, was capable of forming a junction of the two seas or of furnishing the means of carrying out such an undertaking. 353. Old Panama sacked by Morgan and the present city founded. From that time on, the city of Panama increased in wealth and population in consequence of its commercial importance. Trade was established with the west coast of South America and with the ports on the Pacific coast of Central America. In spite of the fact that it was made by the Spaniards a fortress second in strength in America only to old Cartagena, it was sacked and burned by Morgan's buccaneers in February, 1671. The new city, that is the present city, was founded in 1673. It not being considered advisable to rebuild on the old site. View of the harbor of Cologne. 354. The beginnings of the French enterprise. The project of a canal on this route was kept alive for more than 3 centuries by agitations sometimes active and sometimes apparently dying out for long periods, until there was organized in Paris, in 1876, a company entitled Société Civile Internationale du Canal Interoceanique, with General Etienne Tour as president, for the purpose of making surveys and explorations for a ship canal between the two oceans on this route. 355. The Wise Concession and International Congress of 1879. The work on the isthmus for this company was prosecuted under the direction of Lieutenant L.N.B. Wise, a French naval officer, and he obtained for his company in 1878 a concession from the Colombian government, conferring the requisite rights and privileges for the construction of a ship canal on the Panama route and the authority to do such other things as might be necessary or advisable in connection with that project. This concession is ordinarily known as the Wise Concession. A general plan for this Transisthmian Canal was the subject of consideration at an international scientific congress convened in Paris in May, 1879, and composed of 135 delegates from France, Germany, Great Britain, the United States, and other countries, but the majority of whom were French. This Congress was convened under the auspices of Ferdinand de Lesseps, and after remaining in session for 2 weeks a decision, not unanimous, was reached that an international canal ought to be located on the Panama route, and that it should be a sea-level canal without locks. The fact was apparently overlooked that the range between high and low tides in the Bay of Panama, about 20 feet, was so great as to require a tidal lock at that terminus. 356. The plan without locks of the old Panama Canal Companied. A company entitled Compagnie Universelle du Canal Interoceanique was organized, with Ferdinand de Lesseps as president, immediately after the adjournment of the International Congress. The purpose of this company was the construction and operation of the canal, and it purchased the Wise Concession from the original company for the sum of 10 million francs. An immediate but unsuccessful attempt was made to finance the company in August 1879. This necessitated a second attempt, which was made in December 1880, with success, as the entire issue of 600,000 shares of 500 francs each was sold. 2 years were then devoted to examinations and surveys and preliminary work upon the canal, but it was 1883 before operations upon a large scale were begun. The plan adopted and followed by this company was that of a sea-level canal, affording a depth of 29.5 feet and a bottom width of 72 feet. It was estimated that the necessary excavation would amount to 157 million cubic yards. The Atlantic terminus of this canal route was located at Colón, and at Panama on the Pacific side. The line passed through the low grounds just north of Monkey Hill to Gatun, 6 miles from the Atlantic terminus, and where it first met the Chagres River. For a distance of 21 miles it followed the general course of the Chagres to Obispo, but left it at the latter point and passing up the valley of a small tributary cut through the Continental Divide at Culebra, and descended thence by the valley of the Rio Grande to the mouth of that river where it enters Panama Bay. The total length of this line from 30 feet depth in the Atlantic to the same depth in the Pacific was about 47 miles. The maximum height of the Continental Divide on the center line of the canal in the Culebra Cut was about 333 feet above the sea, which is a little higher than the lowest point of the divide in that vicinity. Important considerations in connection with the adjacent alignment made it advisable to cut the divide at a point not its lowest. Old dredges near Colón. 357. The control of the floods in the Chagres. Various schemes were proposed for the purpose of controlling the floods of the Chagres River, the suddenness and magnitude of which were at once recognized as among the greatest difficulties to be encountered in the construction of the work. Although it was seriously proposed at one time to control this difficulty by building a dam across the Chagres at Gamboa, that plan was never adopted, and the problem of control of the Chagres floods remained unsolved for a long period. 358. Estimate of time and cost, appointment of liquidators. It was estimated by de Lesseps in 1880 that 8 years would be required for the completion of the canal, and that its cost would be $127,600,000. The company prosecuted its work with activity until the latter part of 1887, when it became evident that the sea-level plan of canal was not feasible with the resources at its command. Changes were soon made in the plans, and it was concluded to expedite the completion of the canal by the introduction of locks, deferring the change to a sea-level canal until some period when conditions would be sufficiently favorable to enable the company to attain that end. Work was prosecuted under this modified plan until 1889, when the company became bankrupt and was dissolved by judgment of the French court called the Tribunal Civil de la Seine, on February 4, 1889. An officer, called the liquidator, corresponding quite closely to a receiver in this country, was appointed by the court to take charge of the company's affairs. At no time was the project of completing the canal abandoned, but the liquidator gradually curtailed operations and finally suspended the work on May 15, 1889. 359. The Commission d'étude. He determined to take into careful consideration the feasibility of the project, and to that end appointed a Commission d'études, composed of 11 French and foreign engineers, headed by Inspector General Guillaumin, director of the École Nationale de Ponts et Chaussées. This commission visited the isthmus and made a careful study of the entire enterprise, and subsequently submitted a plan for the canal involving locks. The cost of completing the entire work was estimated to be $112,500,000, but the sum of $62,100,000 more was added to cover administration and financing, making a total of $174,600,000. This commission also gave an approximate estimate of the value of the work done and of the plant at $87,300,000, to which some have attached much more importance than did the commission itself. The latter appears simply to have made the estimate 1/2 of the total cost of completing the work added to that of financing and administration, as a loose approximation, calling it an intuitive estimate. In other words, it was simply a guess based upon such information as had been gained in connection with the work done on the isthmus. The partially completed Panama Canal, about 8 miles from Colón. 360. Extensions of time for completion. By this time the period specified for completion under the original Weiss concession had nearly expired. The liquidator then sought from the Colombian government an extension of 10 years, which was granted under the Colombian law dated December 26, 1890. This extension was based upon the provision that a new company should be formed and work on the canal resumed not later than February 28, 1893. The latter condition was not fulfilled, and a second extension was obtained on April 4, 1893, which provided that the 10-year extension of time granted in 1890 might begin to run at any time prior to October 31, 1894, but not later than that date. When it became apparent that the provisions of this last extension would not be carried out, an agreement between the Colombian government and the New Panama Company was entered into on April 26, 1900, which extended the time of completion to October 31, 1910. The validity of this last extension of time has been questioned. 361. Organization of the New Panama Canal Company, 1894. A new company, commonly known as the New Panama Canal Company, was organized on the 20th of October, 1894, with a capital stock of 650,000 shares of 100 francs each. Under the provisions of the Agreement of December 26, 1890, authorizing an extension of time for the construction of the canal, 50,000 shares passed as full paid stock to the Colombian government, leaving the actual working capital of the New Panama Company at 60 million francs, that amount having been subscribed in cash. The most of this capital stock was subscribed for by certain loan associations, administrator, contractors, and others against whom suits had been brought in consequence of the financial difficulties of the old company, it having been charged in the scandals attending bankruptcy proceedings that they had profited illegally. Those suits were discontinued under agreements to subscribe by the parties interested to the capital stock of the new company. The sums thus obtained constituted more than two-thirds of the 60 million francs remaining of the share capital of the new company after the Colombian government received its 50,000 shares. The old company had raised by the sale of stock and bond not far from $246 million, and the number of persons holding the securities thus sold has been estimated at over 200,000. 362. Priority of the Panama Railroad Concession. The Panama Railroad Company holds a concession from the Colombian government, giving it rights prior to those of the Wise Concession, so that the latter could not become effective without the concurrence of the Panama Railroad Company. This is shown by the language of Article 3 of the Wise Concession, which reads as follows: If the line of the canal to be constructed from sea to sea should pass to the west and to the north of the imaginary straight line which joins Cape Tiburon with Garachine Point, the grantees must enter into some amicable arrangement with the Panama Railroad Company or pay an indemnity, which shall be established in accordance with the provisions of Law 46 of August 16, 1867, approving the contract. Celebration on July 5, 1867, reformatory of the contract of April 15, 1850, for the construction of an iron railroad from one ocean to the other through the Isthmus of Panama. It became necessary, therefore, in order to control this feature of the situation, for the old Panama Company to secure at least a majority of the stock of the Panama Railroad Company. As a matter of fact, the old Panama Canal Company purchased nearly 69,000 out of the 70,000 shares of the Panama Railroad Company, each such share having a par value of $100. These shares of Panama Railroad stock are now held in trust for the benefit of the new Panama Canal Company. A part of the expenditures of the old company therefore covered the cost of the Panama Railroad Company's shares, now held in trust for the benefit of the new company. 363. Resumption of work by the new company, the Engineering Commission and the Comite Technique. Immediately after its organization, the new Panama Canal Company resumed the work of excavation in the Emperador and Culebra cuts with a force of men which has been reported as varying between 1,900 and 3,600. It also gave thorough consideration to the subject of the best plan for the completion of the canal. The company's charter provided for the appointment of a special engineering commission of 5 members by the company and the liquidator to report upon the work done and the conclusions to be drawn from its study. This report was to be rendered when the amount expended by the new company should reach about 1/2 of its capital. At the same time, the company also appointed a Comite Technique, constituted of 14 eminent European and American engineers, to make a study of the entire project, which was to avail itself of existing data and the results of such other additional surveys and examinations as it might consider necessary. The report rendered by this committee was elaborate, and it was made November 16, 1898. It was referred to the statutory commission of 5 to which reference has already been made, which commission reported in 1899 that the canal could be constructed within the limits of time and money estimated. On December 30, 1899, a special meeting of the stockholders of the new company was called, but the liquidator, who was one of the largest stockholders, declined to take part in it, and the report consequently has not received the required statutory consideration. The excavation at the Bohio Lock site. 364. Plan of the new company. The plan adopted by the company placed the minimum elevation of the summit level of the canal at 97.5 feet above the sea, and a maximum at 102.5 feet above the same datum. It provided for a depth of 29.5 feet of water and a bottom width of canal prism of about 98 feet, except at special places where this width was increased. A dam was to be built near Bohio, which would thus form an artificial lake with its surface varying from 52.5 to 65.6 feet above the sea. Under this plan there would be a flight of 2 locks at Bohio, about 16 miles from the Atlantic end of the canal, and another flight of 2 locks at Obispo about 14 miles from Bohio, thus reaching the summit level, a single lock at Paraiso, between 6 and 7 miles from Obispo, a flight of 2 locks at Pedro Miguel about 1.25 miles from Paraiso, and finally a single lock at Miraflores, 1.25 miles from Pedro Miguel, bringing the canal down to the ocean elevation. The location of this line was practically the same as that of the old company. The available length of each lock chamber was 738 feet, while the available width was 82 feet, the depth in the clear being 32 feet 10 inches. The lifts were to vary from 26 to 33 feet. It was estimated that the cost of finishing the canal on this plan would be $101,850,000, exclusive of administration and financing. In order to control the floods of the Chagres River, and to furnish a supply of water for the summit level of the canal, a dam was planned to be built at a point called Alhajuela, about 12 miles from Obispo, from which a feeder about 10 miles long, partly an open canal and partly in tunnels or pipe, would conduct the water from the reservoir thus formed to the summit level. 365. Alternative plan of the new Panama Canal Company. Although the plan as described was adopted, the Comite technique apparently favored a modification by which a much deeper excavation through Culebra Hill would be made, thus omitting the locks at both Obispo and Paraiso, and making the level of the artificial Lake Bohio the summit level of the canal. In this modified plan the bottom of the summit level would be about 32 feet above the sea, and the minimum elevation of the summit level 61.5 feet above the sea. This modification of plan had the material advantage of eliminating both the Obispo and Paraiso locks. The total estimated cost of completing the canal under this plan was about $105,500,000. Although the Alhajuela feeder would be omitted, the Alhajuela reservoir would be retained as an agent for controlling the Chagres floods and to form a reserve water supply. The difference in cost of these two plans was comparatively small, but the additional time required to complete that with the lower summit level was probably one of the main considerations in its rejection by the committee having it under consideration. 366. The Isthmian Canal Commission and its work. This brings the project up to the time when the Isthmian Canal Commission was created in 1899 and when the forces of the new Panama Canal Company were employed either in taking care of the enormous amount of plant bequeathed to it by the old company or in the great excavation at Emperador and Culebra. The total excavation of all classes, made up to the time when that commission rendered its report, amounted to about 77 million cubic yards. The work of the commission consisted of a comprehensive and detailed examination of the entire project and all its accessories, as contemplated by the new Panama Canal Company, and any modifications of its plans, either as to alignment, elevations, or subsidiary works, which it might determine advisable to recommend. In the execution of this work it was necessary, among other things, to send engineering parties on the line of the Panama route for the purpose of making surveys and examinations necessary to confirm estimates of the new Panama Canal Company as to quantities, elevations, or other physical features of the line selected, or required in modifications of alignment or plans. In order to accomplish this portion of its work the Commission placed 5 working parties on the Panama route with 20 engineers and other assistants and 41 laborers. The French location for the Bohio Dam. 367. The route of the Isthmian Canal Commission that of the New Panama Canal Company. The Commission adopted for the purposes of its plans and estimates the route selected by the New Panama Canal Company, which is essentially that of the old company. Starting from the 6-fathom contour in the harbor of Colón, the line follows the low marshy ground adjoining the Bay of Limón to its intersection with the Mindy River, thence through the low ground continuing to Gatún, about 6 miles from Colón, where it first meets the Chagres River. From this point to Obispo the canal line follows practically the general course of the Chagres River, although at one point in the marshes below Bohio it is nearly 2 miles from the farthest bend in the river, at a small place called Ahorca Lagarto. Bohio is about 17 miles from the Atlantic terminus, and Obispo about 30 miles. At the latter point the course of the Chagres River, passing upstream, lies to the northeast, while the general direction of the canal line is southeast toward Panama, the latter leaving the former at this location. The canal route follows up the general course of a small stream called the Camacho for a distance of nearly 5 miles where the Continental Divide is found, and in which the Great Culebra Cut is located, about 36 miles from Colón and 13 miles from the Panama terminus. After passing through the Culebra Cut the canal route follows the course of the Rio Grande River to its mouth at Panama Bay. The mouth of the Rio Grande, where the canal line is located, is about 1.5 miles westerly of the city of Panama. The Rio Grande is a small, sluggish stream throughout the last 6 miles of its course, and for that distance the canal excavation would be made mostly in soft silt or mud. Although the line selected by the French company is that adopted by the Isthmian Canal Company for its purposes, a number of most important features of the general plan have been materially modified by the Commission, as will be easily understood from what has already been stated in connection with the French plans. 368. Plan for a sea-level canal. The feasibility of a sea-level canal, but with a tidal lock at the Panama end, was carefully considered by the Commission, and an approximate estimate of the cost of completing the work on that plan was made. In round numbers this estimated cost was about $250 million, and the time required to complete the work would probably be nearly or quite twice that needed for the construction of a canal with locks. The Commission therefore adopted a project for the canal with locks. Both plans and estimates were carefully developed in accordance therewith. 369. Colón Harbor and Canal Entrance. The harbor of Colón has been fairly satisfactory for the commerce of that port, but it is open to the north, and there are probably 2 or 3 days in every year during which northers blow into the harbor with such intensity that ships anchored there must put to sea in order to escape damage. The western limit of this harbor is an artificial point of land formed by material deposited by the old Panama Canal Company. It is called Christophe Colón, and near its extreme end are 2 large frame residences built for de Lesseps. The entrance to the canal is immediately south of this artificial point. The Commission projected a canal entrance from the 6-fathom contour in the Bay of Limón, in which the harbor of Colón is found, swinging on a gentle curve, 6,560 feet radius, to the left around behind the artificial point just mentioned and then across the shoreline to the right into the lowlands southerly of Colón. This channel has a width of 500 feet at the bottom with side slopes of 1:3, except on the second curve, which is somewhat sharper than the first, where the bottom width is made 800 feet for a length of 800 feet for the purpose of a turning basin. This brings the line into the canal proper, forming a well-protected harbor for nearly a mile inside of the shoreline. The distance from the 6-fathom line to this interior harbor is about 2 miles. The total cost of constructing the channel into the harbor and the harbor itself is $8,057,707, and the annual cost of maintenance is placed at $30,000. The harbor would be perfectly protected from the northers which occasionally blow with such intensity in the Bay of Limón, and it could readily be made in all weathers by vessels seeking it. 370. Panama Harbor and Entrance to Canal. The harbor at the Pacific end of the channel where it joins Panama Bay is of an entirely different character in some respects. The Bay of Panama is a place of light winds. Indeed, it has been asserted that the difficulties sometimes experienced by sailing vessels in finding wind enough to take them out of Panama Bay are so serious as to constitute a material objection to the location for a ship canal on the Panama route. This difficulty undoubtedly exists at times, but the simple fact is to be remembered that Panama was a port for sailing ships for more than 200 years before a steamship was known. The harbor of Panama, as it now exists, is a large area of water at the extreme northern limit of the bay, immediately adjacent to the city of Panama, protected from the south by the three islands of Perico, Naos, and Culebra. It has been called a roadstead. There is good anchorage for heavy draft ships, but for the most part the water is shallow. With the Commission's requirement of a minimum depth of water of 35 feet, a channel about 4 miles long from the mouth of the Rio Grande to the 6-fathom line in Panama Bay must be excavated. This channel would have a bottom width of 200 feet with side slopes of 1:3 where the material is soft. Considerable rock would have to be excavated in this channel. At 4.41 miles from the 6-fathom line is located a wharf at the point called La Boca. A branch of the Panama Railroad Company runs to this wharf, and at the present time deep draft ships lie up alongside of it to take on and discharge cargo. The wharf is a steel frame structure, founded upon steel cylinders, carried down to bedrock by the pneumatic process. Its cost was about $1,284,000. The total cost of the excavated channel leading from Panama Harbor to the pier at La Boca is estimated by the Commission at $1,464,513. As the harbor at Panama is considered an open roadstead, it requires no estimate for annual cost of maintenance. The Bohio Dam Site. 371. The route from Colón to Bohio. Starting from the harbor of Colón, the prism of the canal is excavated through the low and for the most part marshy ground to the little village called Bohio. The prism would cut the Shakers River at a number of points, and would require a diversion channel for that river for a distance of about 5 miles on the westerly side of the canal. Levees, or protective embankments, would also be required on the same side of the canal between Bohio and Gatun, the Shakers River leaving the canal line at the latter point on its way to the sea. 372. The Bohio Dam. The principal engineering feature of the entire route is found at Bohio. It is the great dam across the Shakers River at that point, forming Lake Bohio, the summit level of the canal. The new Panama Canal Company located this dam at a point about 17 miles from Colón, and designed to make it an earth structure suitably paved on its faces, but without any other masonry feature. Some borings had been made along the site, and test pits were also dug by the French engineers. It was the conviction of the Isthmian Canal Commission, however, that the character of the proposed dam might be affected by a further examination of the subsurface material at the site. Consequently, the boring parties of the Commission sunk a large number of boreholes at 6 different sections or possible sites along the river in the vicinity of the French location. These borings revealed great irregularity in the character and disposition of the material below the bed and banks of the river. In some places the upper stratum of material was almost clear clay, and in other places clear sand, while all degrees of admixture of clay and sand were also found. At the French site the bedrock at the deepest point is 143 feet below sea level, with large masses of pervious and semi-pervious sand, gravel, and mixtures of those materials with clay. Apparently there is a geological valley in the rock along the general course of the Shakers River in this vicinity filled with sand, gravel, and clay, irregularly distributed and with all degrees of admixture, large masses in all cases being of open texture and pervious to water. The site adopted by the Commission for the purposes of its plans and estimates is located nearly half a mile down the course of the river from that selected by the new Panama Canal Company. The geological valley is nearly 2,000 feet wide at this location, but the deepest rock disclosed by the borings of the Commission is but 128 feet below sea level. The actual channel of the river is not more than 150 feet wide and lies on the extreme easterly side of the valley. The easterly or right bank of the river at this place is clean rock and rises abruptly to an elevation of about 40 feet above the river surface at ordinary stages. The left or westerly bank of the river is compacted clay and sand, and rises equally as abruptly as the rocky bank of the other side, and to about the same elevation. From the top of the abrupt sandy clay bank a plateau of rather remarkable uniformity of elevation extends for about 1,200 feet in a southwesterly direction to the rocky hill in which the Bohio Locks would be located. The rock slope on the easterly or northerly bank of the river runs down under the sandy river bed, but at such an inclination that within the limits of the channel the deepest rock is less than 100 feet below sea level. Profile of Bohio Dam site, selected for plans and estimate, with section of dam. After the completion of all its examinations and after a careful study of the data disclosed by them, the Commission deemed it advisable to plan such a dam as would cut off absolutely all possible subsurface flow or seepage through the sand and gravel below the river surface. It is to be observed that such a subsurface flow might either disturb the stability of an earth dam or endanger the water supply of the summit level of the canal or both. The plan of dam finally adopted by the Commission for the purposes of its estimates is shown by the accompanying plans and sections. A heavy core wall of concrete masonry extends from bedrock across the entire geological valley to the top of the structure, or to an elevation of 100 feet above sea level, thus absolutely closing the entire valley against any possible flow. The thickness of this wall at the bottom is 30 feet, but at an elevation of 30 feet below sea level its sides begin to batter at such a rate as to make the thickness of the wall 8 feet at its top. On either side of this wall are heavy masses of earth embankment of selected material properly deposited in layers with surface slopes of 1:3. As shown by the plans, the lower portions of the core wall of this dam would be sunk to bedrock by the pneumatic process, the joints between the caissons being closed and sealed by cylinders sunk in recesses or wells, also as shown by the plans. 373. Variation in surface elevation of Lake De. The profile of this route shows that the summit level would have an ordinary elevation of 85 feet above the sea, but it may be drawn down for uses of the canal to a minimum elevation of 82 feet above the same datum. On the other hand, under circumstances to be discussed later, it may rise during the floods of the Shakers to an elevation of 90 or possibly 91 or 92 feet above the level of the sea. The top of the dam therefore would be from 8 to 10 feet above the highest possible water surface in the lake, which is sufficient to guard against wash or overtopping of the dam by waves. The total width of the dam at its top would be 20 feet, and the entire inner slope would be paved with heavy riprap suitably placed and bedded. 374. Extent of Lake Bohio and the canal line in it. This dam would create an artificial lake having a superficial area during high water of about 40 square miles. The water would be backed up to a point called Alhajuela, about 25 miles up the river from Bohio. For a distance of nearly 14 miles, i.e., from Bohio to Obispo, the route of the canal would lie in this lake. Although the water would be from 80 to 90 feet deep at the dam for several miles below Obispo, it would be necessary to make some excavation along the general course of the Shakers in order to secure the minimum depth of 35 feet for the navigable channel. Location of the proposed Alhajuela Dam on the Upper Shakers. 375. The floods of the Shakers. The feature of Lake Bohio of the greatest importance to the safe and convenient operation of the canal is that by which the floods of the river Shakers are controlled or regulated. That river is but little less than 150 miles long, and its drainage area, as nearly as can be estimated, contains about 875 square miles. Above Bohio its current moves some sand and a little silt in times of flood, but usually it is a clear water stream. In low water its discharge may fall to 350 cubic feet per second. As is well known, the floods of the Shakers have at times been regarded as almost if not quite insurmountable obstacles to the construction of a canal on this line. The greatest flood of which there is any semblance of a reliable record is one which occurred in 1879. No direct measurements were made, but it is stated with apparent authority that the flood elevation at Bohio was 39.3 feet above low water. If the total channel through which the flood flowed at that time had been as large as at present, actual gaugings or measurements of subsequent floods show that the maximum discharge in 1879 might have been at the rate of 136,000 cubic feet per second. As a matter of fact, the total channel section in that year was less than it is at the present time. Hence, if it be assumed that a flood of 140,000 cubic feet per second must be controlled, an error on the safe side will be committed. Other great floods of which there are reliable records are as follows: 1885 height at Bohio 33.8 feet above low water. 1888, 34.7 1890, 32.1 1893, 28.5. The maximum measured rate of the 1890 flood was 74,998 cubic feet per second, and that of 1893, 48,975 cubic feet per second. It is clear, therefore, that a flood flow of 75,000 cubic feet per second is very rare, and that a flood of 140,000 cubic feet per second exceeds that of which we have any record for practically 40 years. 376. The Gigante Spillway or Waste Weird. It is obvious that the dam, as designed by the Commission, is of such character that no water must be permitted to flow over its crest, or even in immediate proximity to the downstream embankment. Indeed, it is not intended by the Commission that there shall be any wasteway or discharge anywhere near the dam. At a point about 3 miles southwest of the site of the dam at Bohio is a low saddle or notch in the hills near the headwaters of a small stream called the Gigante River. The elevation of this saddle or notch is such that a solid masonry weir with a crest 2,000 feet long may readily be constructed with its foundations on bedrock without deep excavation. This structure is called the Gigante Spillway, and all surplus flood waters from the shakers would flow over it. The waters discharged would flow down to and through some large marshes, one called Pena Blanca and another Agua Clara, before rejoining the shakers. Inasmuch as the canal line runs just easterly of those marshes, it would be necessary to protect it with the levees or embankments to which allusion has already been made. These embankments are neither much extended nor very costly for such a project. The protection of the canal would be further aided by a short artificial channel between the two marshes, Pena Blanca and Agua Clara, for which provision is made in the estimates of the Commission. After the surplus waters from the Gigante Spillway pass these marshes, they again enter the Shakers River or flow over the low, half-submerged country along its borders, and thence through its mouth to the sea near the town of Shakers, about 6 miles northwest of Gatun. 377. Storage in Lake Bohio for driest dry season. The masonry crest of the Gigante Spillway would be placed at an elevation of 85 feet above the sea, identically the same as that which may be called the normal summit level of the canal. It is estimated that the total uses of water in the canal added to the loss by evaporation, taken at 6 inches in depth per month, from the surface of the lake will amount to about 1,070 cubic feet per second if the traffic through the canal should amount to 10 million tons per annum in ships of ordinary size. This draft per second is the sum of 406 cubic feet per second for lockage, 207 for evaporation, 250 for leakage at lock gates, and 200 for power and other purposes, making a total of 1063, which has been taken as 1070 cubic feet per second. The amount of storage in Lake Bohio between the elevations of 85 and 82 feet above sea level, as designed, is sufficient to supply the needs of that traffic in excess of the smallest recorded low water flow of the Shakers River during the dry season of a low rainfall year. The lowest monthly average flow of the Shakers on record at Bohio is 600 cubic feet per second for March, 1891, and for the purposes of this computation that minimum flow has been supposed to continue for 3 months. This includes a sensible margin of safety. In not even the driest year, therefore, can it be reasonably expected that the summit level of the canal would fall below the elevation of 82 feet until the total traffic of the canal carried in ships of the present ordinary size shall exceed 10 million tons. If the average size of ships continues to increase, as will probably be the case, less water in proportion to tonnage will be required for the purposes of lockage. This follows from the fact that with a given tonnage the greater the capacity of the ships the less the number required, and consequently the less will be the number of lockages made. The eastern face of the Culebra Cut. 378. Lake Bohio as a flood controller. On the other hand, it can be shown that with a depth of 5 feet of water on the crest of the Gigante Spillway, the discharge of that were 2,000 feet long will be at the rate of 78,260 cubic feet per second. If the floodwaters of the Shakers should flow into Lake Bohio until the head of water on the crest of the Gigante weir rises to 7.5 feet, the rate of discharge over that weir would be 140,000 cubic feet per second, which, as already shown, exceeds at least by a little the highest flood rate on record. The operation of Lake Bohio as a flood controller or regulator is therefore exceedingly simple. The floodwaters of the Shakers would pour into the lake and immediately begin to flow over the Gigante weir, and continue to do so at an increasing rate as the flood continues. The discharge of the weir is augmented by the increasing flood, and decreases only after the passage of the crest of the flood wave. No flood even as great as the greatest supposable flood on record can increase the elevation of the lake more than 92 to 92.5 feet above sea level, and it will only be at long intervals of time when floods will raise that elevation more than about 90 feet above sea level. The control is automatic and unfailingly certain. It prevents absolutely any damage from the highest supposable floods of the Chagres, and reserves in Lake Bohio all that is required for the purposes of the canal and for wastage by evaporation through the lowest rainfall season. The floods of the Chagres, therefore, instead of constituting the obstacle to construction and convenient maintenance of the canal heretofore supposed, are deprived of all their prejudicial effects and transformed into beneficial agents for the operation of the waterway. 379. Effect of highest floods on current and channel in Lake Bohio. The highest floods are of short duration, and it can be stated as a general law that the higher the flood the shorter its duration. The great floods which it is necessary to consider in connection with the maintenance and operation of this canal would last but a comparatively few hours only. The great flood flow of 140,000 cubic feet per second would increase the current in the narrowest part of the canal below Obispo to possibly 5 feet per second for a few hours only, but that is the only inconvenience which would result from such a flood discharge. That velocity could be reduced by additional excavation. 380. Alhajuela Reservoir not needed at opening of canal. Inasmuch as this system of control, devised and adopted by the Isthmian Canal Commission, is completely effective in regulating the Chagres floods, the reservoir proposed to be constructed by the new Panama Canal Company at Alhajuela on the Chagres about 11 miles above Obispo is not required, and the cost of its construction would be avoided. It could, however, as a project be held in reserve. If the traffic of the canal should increase to such an extent that more water would be needed for feeding the summit level, the dam could be built at Alhajuela so as to impound enough additional water to accommodate, with that stored in Lake Bohio, at least 5 times the 10 million annual traffic already considered. Its existence would at the same time act with substantial effect in controlling the Chagres floods and relieve the Gigante spillway of a corresponding amount of duty. 381. Locks on Panama Route. The locks on the Panama Route are designed to have the same dimensions as those in Nicaragua, as was stated in the lecture on that route. The usable length is 740 feet and the clear width 84 feet. They would be built chiefly of concrete masonry, while the gates would be of steel and of the miter type. 382. The Bohio Locks. The Great Dam at Bohio raises the water surface in the canal from sea level in the Atlantic Maritime section to an ordinary maximum of 90 feet above sea level. In other words, the maximum ordinary total lift would be 90 feet. This total lift is divided into 2 parts of 45 feet each. There is therefore a flight of 2 locks at Bohio, indeed there are 2 flights side by side, as the twin arrangement is designed to be used at all lock sites on both routes. The typical dimensions and arrangements of these locks, with the requisite culverts and other features, are shown in the plans and sections between pages 396 and 397, Part 5. They are not essentially different from other great modern ship canal locks. The excavation for the Bohio locks is made in a rocky hill against which the southwesterly end of the proposed Bohio Dam rests, and they are less than 1,000 feet from it. 383. The Pedro Miguel and Miraflores locks. After leaving Bohio Lake at Obispo, a flight of 2 locks is found at Pedro Miguel, about 7.9 miles from the former or 21.5 miles from Bohio. These locks have a total ordinary maximum lift of 60 feet, divided into 2 lifts of 30 feet each. The 5th and last lock on the route is at Miraflores. The average elevation of water between Pedro Miguel and Miraflores is 30 feet above mean sea level. Inasmuch as the range of tide between high and low in Panama Bay is about 20 feet, the maximum lift at Miraflores is 40 feet and the minimum about 20. The twin locks at Miraflores bring the canal surface down to the Pacific Ocean level, the distance from those locks to the 6-fathom curve in Panama Bay being 8.54 miles. There are therefore 5 locks on the Panama route, all arranged on the twin plan, and, as on the Nicaragua route, all are founded on rock. 384. Guard gates near Obispo. Near Obispo a pair of guard gates are arranged so that if it should become necessary to draw off the water from the summit, the level of Lake Bohio would not be affected. 385. Character and stability of the Culebra Cut. An unprecedented concentration of heavy cutting is found between Obispo and Pedro Miguel. This is practically one cut, although the northwesterly end toward Obispo is called the Emperador, while the deepest part at the other end, about 3 miles from Pedro Miguel, is the Great Culebra Cut with a maximum depth on the center line of the canal of 286 feet. On page 93 of the Isthmian Canal Commission's report is the following reference to the material in this cut. There is a little very hard rock at the eastern end of this section, and the western 2 miles are in ordinary materials. The remainder consists of a hard indurated clay, with some softer material at the top and some strata and dikes of hard rock. In fixing the price it has been rated as soft rock, but it must be given slopes equivalent to those in earth. This cut has been estimated on the basis of a bottom width of 150 feet, with side slopes of 1 on 1. When the old Panama Canal Company began its excavation in this cut, considerable difficulty was experienced by the slipping of the material outside of the limits of the cut into the excavation, and the marks of that action can be seen plainly at the present time. This experience has given an impression that much of the material in this cut is unstable, but that impression is erroneous. The clay which slipped in the early days of the work was not drained, and like wet clay in number. Places in this country it slipped down into the excavation. This material is now drained and is perfectly stable. There is no reason to anticipate any future difficulty if reasonable conditions of drainage are maintained. The high faces of the cut will probably weather to some extent, although experience with such clay faces on the isthmus indicates that the amount of such action will be small. As a matter of fact, the material in which the Culebra Cut is made is stable and will give no sensible difficulty in maintenance. The Culebra Cut. 386. Small diversion channels. Throughout the most of the distance between Colón and Bohio on the easterly side of the canal, the French plan contemplated an excavated channel to receive a portion of the waters of the Chagres as well as the flow of 2 smaller rivers, the Gatincillo and the Mindy, so as to conduct them into the Bay of Manzanillo, immediately to the east of Colón. That so-called diversion channel was nearly completed. Under the plan of the Commission it would receive none of the Chagres flow, but it would be available for intercepting the drainage of the high ground easterly of the canal line and the flow of the 2 small rivers named, so that these waters would not find their way into the canal. There are a few other small works of similar character in different portions of the line, all of which were recognized and provided for by the Commission. 387. Length and curvature. The total length of the Panama route from the 6-fathom curve at Colón to the same curve in Panama Bay is 49.09 miles. The general direction of the route in passing from Colón to Panama is from northwest to southeast, the latter point being about 22 miles east of the Atlantic terminus. The depression through which the line is laid is one of easy topography except at the Continental Divide in the Culebra Cut. As a consequence, there is little heavy work of excavation, as such matters go except in that cut. A further consequence of such topography is a comparatively easy alignment, that is, one in which the amount of curvature is not high. The smallest radius of curvature is 3,281 feet at the entrance to the inner harbor at the Colón end of the route, and where the width is 800 feet. The radii of the remaining curves range from 6,234 feet to 19,629 feet. The following table gives all the elements of curvature on the route and indicates that it is not excessive. Number of curves. Length. Radius. Total curvature. Miles. Feet. Degree 1 0.88 19,629 14 17 1.48 13,123 11 0444.22 11,483 111 32 15 11.61 9,842 355 54 2.44 8,202 90 22 1.67 6,562 77 00 1.73 6,234 35 45 1.82 3,281 75 51 20 2.85 771 39 388. Principal items of work to be performed. The principal items of the total amount of work to be performed in completing the Panama Canal, under the plan of the Commission, can be classified as shown in the following table. Dredging 27,659,540 cu yards, dry earth 14,386,954, soft rock 39,893,235, hard rock 8,806,340. Rock underwater 4,891,667, embankment and backfilling 1,802,753, total 97,440,489, concrete 3,762,175 cu yards, granite 13,820, iron and steel 65,248,900 pounds. Excavation in cofferdam 7,260 cu yards, pneumatic work 108,410, 389. Lengths of sections and elements of total cost. The lengths of the various sections of this route and the costs of completing the work upon them are fully set forth in the following table, taken from the Commission's report, as were the two preceding. Total estimated cost. Miles. Cost. Cologne entrance and harbor $2.39, 8,057,707. Harbor to Bohio locks, including levies 14.42, 11,099,839. Bohio locks, including excavation 0.35, 11,567,275. Lake Bohio 13.61, 2,952,154. Obispo Gates 295,434. Culebra section 7.91, 44,414,460. Pedro Miguel locks, including excavation and dam 0.359,081,321. Pedro Miguel level 1.331,192,286. Miraflores locks, including excavation and spillway 205,781,401. Pacific level 8.53, 12,427,971. Bohio dam 6,369,640. Gigante spillway 1,209,419. Pena Blanca outlet 2,448,076. Shakers diversion 1,929,982. Gatun diversion 100,000. Panama Railroad diversion 1,267,500. Total 49.09, 120,194,465. Engineering, police, sanitation, and general contingencies 20%, 24,038,893. Aggregate $144,233,358. The item in this table, called Panama Railroad Diversion, affords provision for the reconstruction of the railroad necessitated by the formation of Lake Bohio. That lake would submerge the present location of the railroad for 14 or 15 miles. The Culebra cut with steamer Deutschland in it. 390. The 20% allowances for exigencies. It will be observed that in the estimates of cost of the canal on both the Nicaragua and the Panama routes, 20% is allowed for engineering, police, sanitation, and general contingencies. For the purposes of comparison, the same percentage to cover these items was used on both routes. As a matter of fact, the large amount of work which has already been performed on the Panama route removes many uncertainties as to the character of material and other features of difficulty which would be disclosed only after the beginning of the work in Nicaragua. It has therefore been contended with considerable basis of reason that a less percentage to cover these uncertainties should be employed in connection with the Panama estimates than in connection with those for the Nicaragua route. Indeed, it might be maintained that the exigencies which increase cost should be made proportional to the length of route and the untried features. On the other hand, both Panama and Cologne are comparatively large centers of population, and, furthermore, there is a considerable population stretched along the line of the Panama Railroad between those points. The climate and the unsanitary condition of practically every center of population in Central America and on the Isthmus contribute to the continual presence of tropical fevers and other diseases contingent upon the existing conditions of life. It is probable, among other things, that yellow fever is always present on the Isthmus. Inasmuch as the Nicaragua route is practically without population, the amount of disease existing along it is exceedingly small, there being practically no people to be sick. The initial expenditure for the sanitation of the cities at the extremities of the Panama route, as well as for the country between, would be far greater for that route than on the Nicaragua. This fact compensates, to a substantial extent at least, for the physical uncertainties on the Nicaragua line. Indeed, a careful examination of all the conditions existing on both routes indicates the reasonableness of applying the same 20% to both total estimates of cost. 391. Value of plant, property, and rights on the isthmus. The preceding estimated cost of $144,233,358 for completing the Panama Canal must be increased by the amount necessary to be paid for all the property and rights of the new Panama Canal Company on the isthmus. A large amount of excavation has been performed, amounting to 77 million cubic yards of all classes of materials, and nearly all the right-of-way has been purchased. The new Panama Canal Company furnished the Commission with a detailed inventory of its entire properties, which the latter classified as follows: 1. Lands not built on. 2. Buildings, 2431 in number, divided among 47 subclassifications. 3. Furniture and stable outfit, with 17 subclassifications. 4. Floating plant and spare parts, with 24 subclassifications. 5. Rolling plant and spare parts, with 17 subclassifications. 6. Plant, stationary and semi-stationary, and spare parts, with 25 subclassifications. 7. Small material and spare parts, with 4 subclassifications. 8. Surgical and medical outfit. 9. Medical stores. 10. Office supplies, stationary. 11. Miscellaneous supplies, with 740 subclassifications. The Commission did not estimate any value for the vast amount of plant along the line of the canal, as its condition in relation to actual use is uncertain, and the most of it would not be available for efficient and economical execution of the work by modern American methods. Again, a considerable amount of excavated material along some portions of the line has been deposited in spoil banks immediately adjacent to the excavation from which it was taken, and would have to be rehandled in forming the increased size of prism contemplated in the Commission's plan. In view of all the conditions affecting it, the Commission made the following estimate of the value of the property of the new Panama Canal Company, as it is now found on the Panama route. Canal excavation $21,020,386. Shakers diversion $178,186. Gatun diversion $1,396,456. Railroad diversion, 4 miles, $300,000. 22,895,028. Contingencies, 20% $4,579,005. Aggregate $27,474,033. Panama Railroad stock at par $6,850,000. Maps, drawings, and records $2,036,324,033. The Commission added 10% to this total to cover omissions, making the total valuation of the property and rights as now existing $40 million. In computing the value of the channel excavation in the above tabulation, it was estimated that the total quantity of excavation which will be of value in the new plan is 39,586,332 cubic yards. 392. Offer of new Panama Canal Company to sell for $40 million. In January 1902, the new Panama Canal Company offered to sell and transfer to the United States government all its property and rights on the isthmus of every description for the estimate of the Commission, viz., $40 million. In order to make a proper comparison between the total costs of constructing the canal on the two routes, it is necessary to add this $40 million to the preceding aggregate of $144,233,358. Making the total cost of the Panama Canal $184,233,358. It will be remembered that the corresponding total cost of the Nicaragua Canal would be $189,864,062. The railroad pier at La Boca, the Panama end of the canal. 393. Annual costs of operation and maintenance. It is obvious that the cost of operating and maintaining a ship canal across the American Isthmus would be an annual charge of large amount. A large organized force would be requisite, and no small amount of material and work of various kinds and grades would be needed to maintain the works in suitable condition. The Commission made very careful and thorough studies to ascertain as nearly as practicable what these comparative costs would be. In doing this, it gave careful consideration to the annual expenditures made in maintaining the various ship canals of the world, including the Suez, Manchester, Kiel, and St. Mary's Falls canals. The conclusion reached was that the estimated annual costs of maintenance and operation could reasonably be taken as follows. For the Nicaragua Canal $3,300,000, for the Panama Canal $2 million, difference in favor of Panama $1,300,000 394. Volcanoes and earthquakes. Much has been written regarding the comparative liability to damage of canal works along these two routes by volcanic or seismic agencies. As is well known, the entire Central American Isthmus is a volcanic region, and in the past a considerable number of destructive volcanic eruptions have taken place at a number of points. There is a line of live volcanoes extending southeasterly through Nicaragua and Costa Rica. Many earthquake shocks have occurred throughout Nicaragua, Costa Rica, and the state of Panama, some of which have done more or less damage in large portions of those districts. At the same time, many buildings which have been injured have not been substantially built. In fact, that has generally been the case. Both routes lie in districts that are doubtless subject to earthquake shocks, but there is little probability that the substantial structures of a canal along either line would be essentially injured by them. The conclusions of the Commission as to this feature of the matter are concisely stated in 3 paragraphs at the top of page 170 of its report. It is possible and even probable that the more accurately fitting portions of the canal, such as the lock gates, may at times be distorted by earthquakes, and some inconvenience may result therefrom. That contingency may be classed with the accidental collision of ships with the gates, and is to be provided for in the same way, by duplicate gates. It is possible also that a fissure might open which would drain the canal, and, if it remained open, might destroy it. This possibility should not be erected by the fancy into a threatening danger. If a timorous imagination is to be the guide, no great work can be undertaken anywhere. This risk may be classed with that of a great conflagration in a city like that of Chicago in 1871, or Boston in 1872. It is the opinion of the Commission that such danger as exists from earthquakes is essentially the same for both the Nicaragua and Panama routes, and that in neither case is it sufficient to prevent the construction of the canal. The Nicaragua route crosses the line of live volcanoes running from northwest to southeast through Central America, and the crater of Ometepe in Lake Nicaragua is about 11 miles only from the line. The eruptions of Pili and Soufriere show that such proximity of possible volcanic action may be a source of great danger, although even the destruction by them does not certainly indicate damage either to navigation or to canal structures at the distance of 11 miles. Whatever volcanic danger may exist lies on the Nicaragua route, for there is no volcano nearer than 175 miles to the Panama route. 395. Hygienic conditions on the two routes. The relative healthfulness of the two routes has already been touched upon. There is undoubtedly at the present time a vast amount of unhealthfulness on the Panama route, and practically none on the Nicaragua route, but this is accounted for when it is remembered, as has also been stated, that there is practically no population on the Nicaragua route and a comparatively large population along the Panama line. There is a widespread, popular impression that the Central American countries are necessarily intensely unhealthful. This is an error, in spite of the facts that the construction of the Panama Railroad was attended with an appalling amount of sickness and loss of life, and that records of many epidemics at other times and in other places exist in nearly all of these countries. There are the best of good reasons to believe that with the enforcement of sanitary regulations, which are now well understood and completely available, the Central American countries would be as healthful as our southern states. A proper recognition of hygienic conditions of life suitable to a tropical climate would work wonders in Central America in reducing the death rate. At the present time, the domestic administration of most of the cities and towns of Nicaragua and Panama, as well as the generality of Central American cities, is characterized by the absence of practically everything which makes for public health, and by the presence of nearly every agency working for the diseases which flourish in tropical climates. When the United States government reaches the point of actual construction of an Isthmian canal, the sanitary features of that work should be administered and enforced in every detail with the rigor of the most exacting military discipline. Under such conditions, epidemics could either be avoided or reduced to manageable dimensions, but not otherwise. The Commission concluded that existing conditions indicate hygienic advantages for the Nicaragua route, although it is probable that no less effective sanitary measures must be taken during construction in the one case than in the other. 396. Time of passage through the canal. The time required for passing through a transisthmian canal is affected by the length, by the number of locks, by the number of curves, and by the sharpness of curvature. The speed of a ship, and consequently the time of passage, is also affected by the depth of water under its keel. It is well known that the same power applied to a ship in deep water of unlimited width will produce a much higher rate of movement than the same power applied to the same ship in a restricted waterway, especially when the draft of the ship is but little less than the depth of water. These considerations have important bearings both upon the dimensions of a ship canal and upon the time required to pass through it. They were most carefully considered by the Commission, as were also such other matters as the delay incurred in passing through the locks on each line, the latter including the delay of slowing or approaching the lock and of increasing speed after passing it, the time of opening and closing the gates, and the time of emptying and filling the locks. It is also evident that ships of various sizes will require different times for their passage. After giving due weight to all these considerations, it was found that what may be called an average ship would require 12 hours for passing through the Panama Canal and 33 hours for passing through the Nicaragua Canal. Approximately speaking, therefore, it may be stated that an average passage through the former waterway will require but 1/3 the time needed for the latter. A street in Panama. 397. Time for completion on the two routes. The time in which an Isthmian canal may be completed and ready for traffic is an element of the problem of much importance. There are two features of the work to be done at Panama, each of which is of sufficient magnitude to affect to a controlling extent the time required for the construction of the canal, viz., the Bohio Dam and the Culebra Cut. Both of these portions of the work may, however, be prosecuted concurrently and with entire independence of each other. There are no such features on the Nicaragua route, although the cut through the divide west of the lake is probably the largest single work on that route. In considering this feature of the matter, it is well to observe that the total amount of excavation and embankment of all grades on the Nicaragua route is practically 228 million cubic yards, while that remaining to be done on the Panama route is but little more than 97 million cubic yards, or 43% of the former. The accompanying figures show the relative quantities of total excavation, concrete, iron, and steel required in construction along the two routes, as well also as the total amounts and radii of curvature. Diagrams comparing some of the main elements of the two routes. The Commission has estimated 10 years for the completion of the canal on the Panama route and 8 years for the Nicaragua route, including in both cases the time required for preparation and that consumed by unforeseen delays. The writer believes that the actual circumstances attending work on the two routes would justify an exchange of these time relations. There is great concentration of work in the Culebra Emperador Cut on the Panama route, covering about 45% of the total excavation of all grades, 43 million cubic yards, which is distributed over a distance of about 7 miles, with the location of greatest intensity at Culebra. This demands efficient organization and special plant so administered as to reduce the working force to an absolute minimum by the employment of machinery to the greatest possible extent. A judicious, effective organization and plant would transform the execution of this work into what may be called a manufactory of excavation, with all the intensity of direction and efficiency of well-designed and administered machinery which characterizes the concentration of labor and mechanical appliances in great manufacturing establishments. Such a successful installation would involve scarcely more advance in contract operations than was exhibited, in its day, in the execution of the work on the Chicago Drainage Canal. By such means only can the peculiar difficulties attendant upon the execution of great works in the tropics be reduced to controllable dimensions. The same general observations may be applied to the construction of the Bohio Dam, even should a no more favorable site be found, The greatest concentration of excavation on the Nicaragua route is between the lake and the Pacific, but it constitutes only 10% of the total excavation of all grades, and it can be completed in far less time than the Great Cut on the Panama route. If this were the only great feature of work besides the dam, the time for completion of work on this route would be materially less than that required for the Panama crossing. As a matter of fact, there are a succession of features of equivalent magnitude, or very nearly so, from Greytown nearly to Brito, extending over a distance of at least 175 miles, requiring the construction of a substantial service railroad over a considerable portion of the distance prior to the beginning of work. This attenuation of work requires the larger features to be executed in succession to a considerable extent, or much duplication of plant and the employment of a great force of laborers, practically all of whom must be foreigners, housed, organized, and maintained in a practically uninhabited tropical country where many serious difficulties reach a maximum. It is not within the experience of civil engineers to execute by any practicable means that kind of a program on schedule time. The weight of this observation is much increased when it is remembered that the total volume of work may be taken nearly twice as great in Nicaragua as at Panama, and that large portions between Lake Nicaragua and the Caribbean Sea must be executed in a region of continual and enormous rainfall. It would seem more reasonable to the writer to estimate 8 years for the completion of the Panama Canal and 10 years for the completion of the Nicaragua Canal. 398. Industrial and commercial value of the canal. The prospective industrial and commercial value of the canal also occupied the attention of the Commission in a broad and careful study of the elements which enter that part of the problem. It is difficult if not impossible to predict just what the effect of a Isthmian canal would be either upon the ocean commerce of the United States or of other parts of the world, but it seems reasonable to suppose from the result of the Commission's examinations that had the canal been in existence in 1899 at least 5 million tons of the actual traffic of that year would have been accommodated by it. The opening of such a waterway, like the opening of all other traffic routes, induces the creation of new traffic to an extent that cannot be estimated, but it would appear to be reasonable to suppose that within 10 years from the date of its opening the vessel tonnage using it would not be less than 10 million tons. View of Panama. The Nicaragua route would favor in distance the traffic between our Atlantic, including Gulf, and Pacific ports. The distances between our Atlantic ports and San Francisco would be about 378 nautical miles less than by Panama. Between New Orleans and San Francisco, this difference in favor of the route by Greytown and Brito would be 580 nautical miles. It must be remembered, however, that the greater time by at least 24 hours required for passage through the Nicaragua Canal practically obliterates this advantage, and in some cases would throw the advantage in favor of the Panama waterway. This last observation would hold with particular force if for any reason a vessel should not continue her passage, or should continue it at a reduced speed during hours of darkness, which could not be escaped on the Nicaragua Canal, but might be avoided at Panama. For all traffic between the Atlantic, including Gulf, ports and the west coast of South America, the Panama crossing would be the most advantageous. As a matter of fact, while there may be some small advantage in miles by one route or the other for the traffic between some particular points, on the whole neither route would have any very great advantage over the other in point of distance or time. Either would serve efficiently the purposes of all ocean traffic in which the ports of the United States are directly interested. The effect of this ship waterway upon the well-being of the United States is not altogether of a commercial character. As indicated by the Commission, this additional bond between the two portions of the country will have a beneficial effect upon the unity of the political interests as well as upon the commercial welfare of the country. Indeed, it is the judgment of many well-informed people that the commercial advantages resulting from a closer touch between the Atlantic and Pacific coasts of the country are of less consequence than the unifying of political interests. In a final comparison between the two routes, it is to be remembered that the concession under which the new Panama Company has been and is now prosecuting its work is practically valueless for the purposes of this country. It will therefore be necessary to secure from the Republic of Colombia, for the Panama route, as well as from the republics of Nicaragua and Costa Rica, for the Nicaragua route, such new concessions as may be adequate for all the purposes of the United States in the construction of this Isthmian canal. The cost of those concessions in either case must be added to the estimated total cost of the work, as set forth, in order to reach the total cost of the canal along either route. 399. Comparison of routes. Concisely stating the situation, its main features may be expressed somewhat as follows. Both routes are entirely practicable and feasible. Neither route has any material commercial advantage over the other as to time, although the distance between our Atlantic, including Gulf, and Pacific ports is less by the Nicaragua route. The Panama route has about 1/4 the length of that in Nicaragua. It has less locks, less elevation of summit level, and far less curvature, all contributing to correspondingly decreased risks peculiar to the passage through a canal. The estimated annual cost of operation and maintenance of the Panama route is but 6/10 that for the Nicaragua route. The harbor features may be made adequate for all the needs of a canal by either route, with such little preponderance of advantage as may exist in favor of the Panama crossing. The Commission estimated 10 years for the completion of the Panama Canal and 8 years for the Nicaragua waterway, but the writer believes that these relations should be exchanged, or at least that the time of completion for the Panama route should not be estimated greater than for the Nicaragua. The water supply is practically unlimited on both routes, but the controlling or regulating works, being automatic, are much simpler and more easily operated and maintained on the Panama route. The Nicaragua route is practically uninhabited, and consequently practically no sickness exists there. On the Panama route, on the contrary, there is a considerable population extending along the entire line, among which yellow fever and other tropical diseases are probably always found. Initial sanitary works of much larger magnitude would be required on the Panama route than on the Nicaragua, although probably as rigorous sanitary measures would be required during the construction of the canal on one route as on the other. The railroad on the Panama route and other facilities offered by a considerable existing population render the beginning of work and the housing and organization of the requisite labor force less difficult and more prompt than on the Nicaragua route. The greater amount of work on the Nicaragua route, and its distribution over a far greater length of line, involve the employment of a correspondingly greater force of laborers, with greater attendant difficulties, for an equally prompt completion of the work. The relative seismic conditions of the two routes cannot be quantitatively stated with accuracy, but in neither case are they of sufficient gravity to cause anxiety as to the effects upon completed canal structures. Concessions and treaties require to be secured and negotiated for the construction of the canal on either route, and under the conditions created by the $40 million offer of the new Panama Canal Company, this feature of both routes appears to possess about the same characteristics, although the Nicaragua route is, perhaps, freer from the complicating shadows of prior rights and concessions. Footnotes. 1. The first permanent water commissioner in Rome was M. Agrippa, son-in-law of Caesar Augustus, who took office BC 34. He was one of the greatest Roman engineers and constructors, if indeed he was not the first in rank. 2. For a complete and detailed statement of this whole subject, including design work, reference should be made to the author's elasticity and resistance of materials. 3. This bridge was designed by and is being constructed under the direction of Messrs. Bowler and Hodge, Consulting Engineers, New York City. 4. Estimated. 5. Compiled, except the figures for London, by Hazen. Engineering News, 1899, XLI. Page 111. 6. Includes added territory. 7. What is generally known as the Michigan Standard of the Purity of Drinking Water, as specified by the Michigan State Laboratory of Hygiene, is here given. 1. The total residue should not exceed 500 parts per million. 2. The inorganic residue may constitute the total residue. 3. The smaller amount of organic residue the better the water. 4. The amount of earthy bases should not exceed 200 parts per million. 5. The amount of sodium chloride should not exceed 20 parts per million, i.e., chlorine 12.1 parts per million. 6. The amount of sulfates should not exceed 100 parts per million. 7. The organic matter in 1 million parts of the water should not reduce more than 8 parts of potassium permanganate, i.e., required oxygen 2.2 parts per million. 8. The amount of free ammonia should not exceed 0.05 part per million. 9. The amount of albuminoid ammonia should not exceed 0.15 part per million. 10. The amount of nitric acid should not exceed 3.5 parts per million, i.e., N as nitrate 0.9 part per million. 11. The best water contains no nitrous acid, and any water which contains the substance in quantity sufficient to be estimated should not be regarded as a safe drinking water. 12. The water must contain no toxicogenic germs as demonstrated by tests upon animals. The water must be clear and transparent, free from smell, and without either alkaline or acid taste, and not above 5 French standard of hardness. This standard is too high to be attained ordinarily in natural waters. 8. By Standard Railroad Signal Company of Troy, N.Y. Transcriber's notes: deprecated spellings were not corrected. The illustrations and tables have been moved so that they do not break up paragraphs and so that they are next to the text they illustrate. Typographical and punctuation errors have been silently corrected. End of the Project Gutenberg ebook. Ancient and Modern Engineering and the Isthmian Canal. Updated editions will replace the previous one, the old editions will be renamed. Creating the works from print editions not protected by U.S. copyright law means that no one owns a United States copyright in these works, so the Foundation, and you, can copy and distribute it in the United States without permission and without paying copyright royalties. Special rules, set forth in the General Terms of Use part of this license, apply to copying and distributing Project Gutenberg electronic works to protect the Project Gutenberg concept and trademark. Project Gutenberg is a registered trademark, and may not be used if you charge for an ebook, except by following the terms of the trademark license, including paying royalties for use of the Project Gutenberg trademark. If you do not charge anything for copies of this ebook, complying with the trademark license is very easy. You may use this ebook for nearly any purpose, such as creation of derivative works, reports, performances, and research. Project Gutenberg ebooks may be modified and printed and given away. You may do practically anything in the United States with ebooks not protected by U.S. copyright law. Redistribution is subject to the trademark license, especially commercial redistribution. Start. Full license. The full Project Gutenberg license. Please read this before you distribute or use this work to protect the Project Gutenberg mission of promoting the free distribution of electronic works, by using or distributing this work, or any other work associated in any way with the phrase Project Gutenberg. You agree to comply with all the terms of the full Project Gutenberg license available with this file or online at www.gutenberg.org/license. Section 1. General Terms of Use and Redistributing Project Gutenberg Electronic Works. 1.a. By reading or using any part of this Project Gutenberg electronic work, you indicate that you have read, understand, agree to and accept all the terms of this license and intellectual property, trademark/copyright, agreement. If you do not agree to abide by all the terms of this agreement, you must cease using and return or destroy all copies of Project Gutenberg electronic works in your possession. If you paid a fee for obtaining a copy of or access to a Project Gutenberg electronic work and you do not agree to be bound by the terms of this agreement, you may obtain a refund from the person or entity to whom you paid the fee as set forth in paragraph 1.e.8. 1.b. Project Gutenberg is a registered trademark. It may only be used on or associated in any way with an electronic work by people who agree to be bound by the terms of this agreement. There are a few things that you can do with most Project Gutenberg electronic works even without complying with the full terms of this agreement. See paragraph 1.c below. There are a lot of things you can do with Project Gutenberg electronic works if you follow the terms of this agreement and help preserve free future access to Project Gutenberg electronic works. See paragraph 1.e below. 1.c. The Project Gutenberg Literary Archive Foundation, the Foundation or PGLAF, owns a compilation copyright in the collection of Project Gutenberg electronic works. Nearly all the individual works in the collection are in the public domain in the United States. If an individual work is unprotected by copyright law in the United States and you are located in the United States, we do not claim a right to prevent you from copying, distributing, performing, displaying or creating derivative works based on the work as long as all references to Project Gutenberg are removed. Of course, we hope that you will support the Project Gutenberg mission of promoting free access to electronic works by freely sharing Project Gutenberg works in compliance with the terms of this agreement for keeping the Project Gutenberg name associated with the work. You can easily comply with the terms of this agreement by keeping this work in the same format with its attached full Project Gutenberg license when you share it without charge with others. 1.d. The copyright laws of the place where you are located also govern what you can do with this work. Copyright laws in most countries are in a constant state of change. If you are outside the United States, check the laws of your country in addition to the terms of this agreement before downloading, copying, displaying, performing, distributing or creating derivative works based on this work or any other Project Gutenberg work. The Foundation makes no representations concerning the copyright status of any work in any country other than the United States. 1.e. Unless you have removed all references to Project Gutenberg. 1.e.1. The following sentence, with active links to, or other immediate access to, the full Project Gutenberg license must appear prominently whenever any copy of a Project Gutenberg work, any work on which the phrase Project Gutenberg appears, or with which the phrase Project Gutenberg is associated, is accessed, displayed, performed, viewed, copied or distributed. This ebook is for the use of anyone anywhere in the United States and most other parts of the world at no cost and with almost no restrictions whatsoever. You may copy it, give it away or reuse it under the terms of the Project Gutenberg license included with this ebook or online at www.gutenberg.org. If you are not located in the United States, you will have to check the laws of the country where you are located before using this ebook. 1.e.2. If an individual Project Gutenberg electronic work is derived from texts not protected by U.S. copyright law, does not contain a notice indicating that it is posted with permission of the copyright holder, the work can be copied and distributed to anyone in the United States without paying any fees or charges. If you are redistributing or providing access to a work with the phrase Project Gutenberg associated with or appearing on the work, you must comply either with the requirements of paragraphs 1.e.1 through 1.e.7 or obtain permission for the use of the work and the Project Gutenberg trademark as set forth in paragraphs 1.e.8 or 1.e.9. 1.e.3. If an individual Project Gutenberg electronic work is posted with the permission of the copyright holder, your use and distribution must comply with both paragraphs 1.e.1 through 1.e.7 and any additional terms imposed by the copyright holder. Additional terms will be linked to the Project Gutenberg license for all works posted with the permission of the copyright holder found at the beginning of this work. 1.e.4. Do not unlink or detach or remove the full Project Gutenberg license terms from this work, or any files containing a part of this work or any other work associated with Project Gutenberg. 1.e.5. Do not copy, display, perform, distribute or redistribute this electronic work, or any part of this electronic work, without prominently displaying the sentence set forth in paragraph 1.e.1 with active links or immediate access to the full terms of the Project Gutenberg license. 1.e.6. You may convert to and distribute this work in any binary, compressed, marked up, non-proprietary or proprietary form, including any word processing or hypertext form. However, if you provide access to or distribute copies of a Project Gutenberg work in a format other than plain vanilla ASCII or other format used in the official version posted on the official Project Gutenberg website, www.gutenberg.org, you must, at no additional cost, fee or expense to the user, provide a copy, a means of exporting a copy, or a means of obtaining a copy upon request, of the work in its original plain vanilla ASCII or other form. Any alternate format must include the full Project Gutenberg license as specified in paragraph 1.e.1. 1.e.7. Do not charge a fee for access to, viewing, displaying, performing, copying or distributing any Project Gutenberg works unless you comply with paragraph 1.e.8 or 1.e.9. 1.e.8. You may charge a reasonable fee for copies of or providing access to or distributing Project Gutenberg electronic works provided that, You pay a royalty fee of 20% of the gross profits you derive from the use of Project Gutenberg works calculated using the method you already use to calculate your applicable taxes. The fee is owed to the owner of the Project Gutenberg trademark, but he has agreed to donate royalties under this paragraph to the Project Gutenberg Literary Archive Foundation. Royalty payments must be paid within 60 days following each date on which you prepare, or are legally required to prepare, your periodic tax returns. Royalty payments should be clearly marked as such and sent to the Project Gutenberg Literary Archive Foundation at the address specified in Section 4, Information about donations to the Project Gutenberg Literary Archive Foundation. You provide a full refund of any money paid by a user who notifies you in writing, or by email, within 30 days of receipt that he does not agree to the terms of the full Project Gutenberg license. You must require such a user to return or destroy all copies of the works possessed in a physical medium and discontinue all use of and all access to other copies of Project Gutenberg works. You provide, in accordance with paragraph 1.f.3, a full refund of any money paid for a work or a replacement copy, if a defect in the electronic work is discovered and reported to you within 90 days of receipt of the work. You comply with all other terms of this agreement for free distribution of Project Gutenberg works. 1.e.9. If you wish to charge a fee or distribute a Project Gutenberg electronic work or group of works on different terms than are set forth in this agreement, you must obtain permission in writing from the Project Gutenberg Literary Archive Foundation, the manager of the Project Gutenberg trademark. Contact the Foundation as set forth in Section 3 below. 1.f.1. Project Gutenberg volunteers and employees expend considerable effort to identify, do copyright research on, transcribe and proofread works not protected by U.S. copyright law in creating the Project Gutenberg collection. Despite these efforts, Project Gutenberg electronic works, and the medium on which they may be stored, may contain defects, such as, but not limited to, incomplete, inaccurate or corrupt data, transcription errors, a copyright or other intellectual property infringement, a defective or damaged disk or other medium, a computer virus, or computer codes that damage or cannot be read by your equipment. 1.f.2. Limited warranty. Disclaimer of damages except for the right of replacement or refund described in paragraph 1.f.3, the Project Gutenberg Literary Archive Foundation, the owner of the Project Gutenberg trademark, and any other party distributing a Project Gutenberg electronic work under this agreement, disclaim all liability to you for damages, costs, and expenses, including legal fees. You agree that you have no remedies for negligence, strict liability, breach of warranty or breach of contract except those provided in paragraph 1.f.3. You agree that the Foundation, the trademark owner, and any distributor under this agreement will not be liable to you for actual, direct, indirect, consequential, punitive or incidental damages even if you give notice of the possibility of such damage. 1.f.3. Limited right of replacement or refund. If you discover a defect in this electronic work within 90 days of receiving it, you can receive a refund of the money, if any, you paid for it by sending a written explanation to the person you received the work from. If you received the work on a physical medium, you must return the medium with your written explanation. The person or entity that provided you with the defective work may elect to provide a replacement copy in lieu of a refund. If you received the work electronically, the person or entity providing it to you may choose to give you a second opportunity to receive the work electronically in lieu of a refund. If the second copy is also defective, you may demand a refund in writing without further opportunities to fix the problem. 1.f.4. Except for the limited right of replacement or refund set forth in paragraph 1.f.3, this work is provided to you ASIS, with no other warranties of any kind, express or implied, including but not limited to warranties of merchantability or fitness for any purpose. 1.f.5. Some states do not allow disclaimers of certain implied warranties or the exclusion or limitation of certain types of damages. If any disclaimer or limitation set forth in this agreement violates the law of the state applicable to this agreement, the agreement shall be interpreted to make the maximum disclaimer or limitation permitted by the applicable state law. The invalidity or unenforceability of any provision of this agreement shall not void the remaining provisions. 1.f.6. Indemnity. You agree to indemnify and hold the foundation, the trademark owner, any agent or employee of the foundation, anyone providing copies of Project Gutenberg electronic works in accordance with this agreement, and any volunteers associated with the production, promotion, and distribution of Project Gutenberg electronic works, harmless from all liability, costs, and expenses, including legal fees, that arise directly or indirectly from any of the following which you do or cause to occur. A. Distribution of this or any Project Gutenberg work. B. Alteration, modification, or additions or deletions to any Project Gutenberg work. And C. Any defect you cause. Section 2. Information about the mission of Project Gutenberg. Project Gutenberg is synonymous with the free distribution of electronic works in formats readable by the widest variety of computers, including obsolete, old, middle-aged, and new computers. It exists because of the efforts of hundreds of volunteers and donations from people in all walks of life. Volunteers and financial support to provide volunteers with the assistance they need are critical to reaching Project Gutenberg's goals and ensuring that the Project Gutenberg collection will remain freely available for generations to come. In 2001, the Project Gutenberg Literary Archive Foundation was created to provide a secure and permanent future for Project Gutenberg and future generations. To learn more about the Project Gutenberg Literary Archive Foundation and how your efforts and donations can help, see Sections 3 and 4 and the Foundation information page at www.gutenberg.org. Section 3. Information about the Project Gutenberg Literary Archive Foundation. The Project Gutenberg Literary Archive Foundation is a nonprofit 501(c)(3) educational corporation organized under the laws of the state of Mississippi and granted tax-exempt status by the Internal Revenue Service. The Foundation's EIN or Federal Tax Identification Number is 64-6221541. Contributions to the Project Gutenberg Literary Archive Foundation are tax-deductible to the full extent permitted by U.S. federal laws and your state's laws. The Foundation's business office is located at 809 North 1500 West, Salt Lake City, Utah, 84116-801-596-1887. Email contact links and up-to-date contact information can be found at the Foundation's website and official page at www.gutenberg.org/contact. Section 4. Information about donations to the Project Gutenberg Literary Archive Foundation. Project Gutenberg depends upon and cannot survive without widespread public support and donations to carry out its mission of increasing the number of public domain and licensed works that can be freely distributed in machine-readable form accessible by the widest array of equipment, including outdated equipment. Many small donations, $1 to $5,000, are particularly important to maintaining tax-exempt status with the IRS. The Foundation is committed to complying with the laws regulating charities and charitable donations in all 50 states of the United States. Compliance requirements are not uniform and it takes a considerable effort, much paperwork, and many fees to meet and keep up with these requirements. We do not solicit donations in locations where we have not received written confirmation of compliance. To send donations or determine the status of compliance for any particular state, visit www.gutenberg.org/donate. While we cannot and do not solicit contributions from states where we have not met the solicitation requirements, we know of no prohibition against accepting unsolicited donations from donors in such states who approach us with offers to donate. International donations are gratefully accepted, but we cannot make any statements concerning tax treatment of donations received from outside the United States. U.S. laws alone swamp our small staff. Please check the Project Gutenberg web pages for current donation methods and addresses. Donations are accepted in a number of other ways, including checks, online payments, and credit card donations. To donate, please visit www.gutenberg.org/donate. Section 5. General information about Project Gutenberg electronic works. Professor Michael S. Hart was the originator of the Project Gutenberg concept of a library of electronic works that could be freely shared with anyone. For 40 years, he produced and distributed Project Gutenberg ebooks with only a loose network of volunteer support. Project Gutenberg ebooks are often created from several printed editions, all of which are confirmed as not protected by copyright in the US unless a copyright notice is included. Thus, we do not necessarily keep ebooks in compliance with any particular paper edition. Most people start at our website, which has the main PG search facility, www.gutenberg.org. This website includes information about Project Gutenberg, including how to make donations to the Project Gutenberg Literary Archive Foundation, how to help produce our new ebooks, and how to subscribe to our email newsletter to hear about new ebooks.